Hello there and welcome to Life Beyond Seen, the place where curiosity settles in beside you, and science moves at a pace that never asks anything of you except to listen. Tonight we're drifting into a part of the world that most people never think about unless they're trying to picture the ocean on a map. We're heading far away from shorelines and reefs and busy coasts, out to regions so empty and so quietly vast that sailors once whispered about them as if they were places the world had forgotten to finish. These stretches of water are sometimes called oceanic deserts, places where the sea looks endless, calm and strangely bare of life. But even in the emptiest water on Earth, something is always stirring, breathing, drifting, simply trying to exist. Before we ease into this deep blue stillness, I'd love to know where you're listening from tonight. Maybe you're near the sea yourself, or maybe you're somewhere completely landlocked where the nearest coastline is just a picture or a memory. Wherever you are, whatever time it happens to be in your corner of the world, thank you for joining this slow exploration. And if these quiet wanderings bring you comfort or help you unwind after a long day, I'd be grateful if you tapped the like button or subscribed. It's a small gesture, but it helps this sleepy little corner reach others who might need a gentle moment too. So take a breath, settle in, and let your mind drift the same way a piece of floating seaweed might drift on a current. Because as empty as these waters appear from above, they hold stories worth unfolding slowly, especially when the world feels loud and rushed. And if you've ever wondered what it truly means for a place to be quiet, the middle of the ocean has a way of answering that without saying a single word. If you picture the ocean, you might imagine coral reefs glowing with fish or coastal bays filled with birds and seagrass. But most of the ocean is nothing like that. Most of it is open water stretching for hundreds or thousands of miles, without so much as a rock for a barnacle to cling to. These are the places where sunlight fades quickly, where nutrients are scarce, and where life has to work harder for every small advantage. They aren't deserts in the sense of sand and dunes, but deserts in the sense that resources are thin and survival depends on strategies built around scarcity. From above, the surface looks calm, but below it lies a world shaped by hunger, distance, and endurance. And maybe that's why these places draw such curiosity. There's something strangely calming about imagining an environment so open that nothing interrupts the horizon. Nothing demands attention. Nothing churns around you the way everyday life so often does. It's just space, water, and time moving steadily forward. Even the creatures that survive there seem adapted not for chaos or spectacle, but for patience and persistence. They drift slowly, feed slowly, grow slowly. If they move at all, they do it with no wasted energy, following currents that have circled the planet long before we ever learned to map them. When sailors crossed these waters centuries ago, they described them as eerily still. Days would pass with no birds, no fish, no seaweed, nothing but open water stretching out in every direction. The calm wasn't peaceful to them, it was unsettling, as if they had slipped into a part of the world where life had taken a long vacation. Their ships cut through water that felt almost too clean, too untouched, and when the wind died, the silence became something they carried with them long after they reached land again. Today we know that these regions aren't empty in the way early travellers believed. They are simply sparse, and sparsity is a different kind of existence altogether. Instead of coral reefs bursting with colour, these waters hold tiny drifters, microscopic organisms that carry out slow but essential work. Instead of dense schools of fish, you find solitary wanderers spaced far apart, each one conserving energy, each one moving with a purpose that we can appreciate, even if we can't fully imagine living that way. If you've ever looked across a wide empty parking lot or a long stretch of quiet highway and felt something shift in your mind, something that slows your thoughts for a moment, you may already understand a piece of what these waters feel like. Not frightening, not lonely, just spacious enough that your attention softens. Nothing competes for it. Nothing insists on being noticed. That's the feeling the open ocean brings, only multiplied by thousands of miles and depths that light can't reach. But before we drift any deeper into what lives there, it's worth pausing on the idea of emptiness itself. When we hear that word, we often imagine something lacking or unfinished. But emptiness in the ocean has a different meaning. It's not a flaw or a void. It's a natural outcome of how nutrients travel, how sunlight reaches the surface, how currents move from one hemisphere to the other, carrying just enough food for a faint, steady web of life. The emptiness is part of the system. It's what makes the busy areas busy and the sparse areas sparse. In that sense, these oceanic deserts mirror our own lives in ways we don't usually think about. Our days have dense places filled with activity, noise, decisions, and rushing from one thing to the next. But we also have quieter parts, the mental open water where nothing demands urgency. Those moments might feel uneventful or unproductive, yet they hold space for reflection, rest, and simple breathing. The ocean reminds us that both types of environments matter, even when we don't give them equal attention. And just as life doesn't vanish in the emptiest parts of the sea, life doesn't disappear in the quieter stretches of our own days. It just shifts shape, operating at a slower scale, less visible but still meaningful. Maybe that's why the middle of the ocean feels like such a fitting place to explore when the world asks a lot from us. It's an environment that insists nothing. It allows you to exist without needing to keep pace with anything except your own thoughts. As we move into the open water, try to imagine the surface around you stretching so far that even the sky starts to feel larger. The horizon becomes a gentle line instead of a boundary. The waves take their time. There's no sound except the soft push of wind through salt air. And beneath the water, in the dim blue where sunlight weakens with every meter, life is scattered so widely that each creature seems almost suspended in its own private world. These are not places of abundance. They are places of endurance, and endurance creates its own quiet rhythm. Floating there, you might not see anything at first. That's part of the experience. These waters don't reveal their stories all at once. They ask you to slow down long enough to notice what's usually overlooked. A faint flicker just below the surface, a single speck drifting with no visible effort, a thin line of distant ripples where something large but unhurried moved past hours earlier. Nothing leaps or splashes the way animals do near coasts. Everything out here seems content with moving precisely as much as it needs to and no more. If you listen closely to the steady sound of the ocean, it becomes almost like breathing. Not dramatic breathing, just a natural rhythm that continues whether you notice it or not. And while you sit with that quiet, the idea of scarcity begins to feel less threatening and more interesting. Creatures that live here do so not because the environment is forgiving, but because they've adapted to scarcity so completely that it becomes their normal. They stretch limited resources in ways that reveal resilience rather than struggle. It's easy to imagine emptiness as a lack of meaning, but out here meaning is shaped by the smallest advantages, the tiniest shifts in light, temperature, and nutrients. A patch of water enriched by a passing current becomes a feast for microscopic life, which then becomes food for something slightly larger. Everything builds slowly, carefully, and when the water thins again, everything returns to waiting. There's no rush. Waiting is part of surviving. And as we drift along, this gentle introduction begins to open into the larger question of the night. What exactly manages to survive in places that seem so bare? How does life persist where there appears to be so little? And what does this tell us about the resilience woven through the natural world in places most of us will never see with our own eyes? Those questions lead naturally into the waters ahead, where the story of oceanic deserts becomes clearer the longer we stay with it. As empty as these regions appear, they hold a kind of quiet complexity that reveals itself one small detail at a time, the same way your thoughts sometimes settle into clarity only after everything else around you slows down. When you imagine the middle of the ocean, it's easy to picture a shade of blue so deep and steady that it almost feels like a pause in the world. Not a dramatic one, not the kind that announces itself, but the quiet kind that settles in gradually. As you move farther from shore, the coastline fades, the water darkens, and the noise of land slips away until even the memories of busy places feel distant. There's a moment during that transition where you notice how the sea changes from something familiar to something more open, and the air begins to feel different. There's nothing to interrupt the horizon, nothing to anchor your gaze except the soft line where sky meets water. This is where the world turns blue, not just in colour, but in the sense that everything around you becomes calm, wide, and unbroken. Out here, the ocean stretches for thousands of miles without a single island, reef, or rock to break the surface. There are no coasts with scattered homes or cliffs or busy harbours, just water moving in every direction. The surface is shaped by long, slow swells that can travel across entire oceans without losing their shape. These swells aren't the dramatic waves you see on stormy beaches. They're the quieter kind, the kind that roll beneath you with a steadiness that doesn't ask for attention. Even the wind behaves differently. Instead of rustling trees or carrying everyday sounds, it moves freely over open water with nothing to interrupt it, giving the impression that the world has grown larger and more spacious than usual. And somewhere in that wide stillness, you notice something else. The ocean in its open middle feels strangely empty compared to the busy shores or the crowded coral reefs we often picture when thinking about marine life. There are no flocks of seabirds gliding overhead. There are no clusters of fish darting around the surface. No plants reach up from the depths. No bright colours flash beneath the water. It creates a sense that life has thinned out, that the sea has quieted itself in ways we rarely see near land. It isn't lifeless, but it gives the impression of an environment that has learned to exist with very little. This sense of emptiness, though, isn't a flaw in the ocean's design. It's the natural result of how the planet distributes nutrients. Near coasts, rivers bring minerals from land, and upwelling currents lift nutrient-rich water from the deep. Those areas burst with opportunities for life. But in the middle of the ocean, far from any coastline and far from most upwelling currents, the surface becomes a clear, nutrient-poor environment. Sunlight reaches the water just fine, but without nutrients, photosynthetic organisms have a harder time surviving. Where those tiny organisms are scarce, everything that depends on them feels the impact. The food web becomes stretched thin, and the creatures that remain must adapt to a life where every small advantage matters. Still, calling these waters empty doesn't quite capture what they are. If you lean over the side of a drifting boat and look down, you won't see nothing. You'll see water so clear that it almost feels weightless, as if depth can be measured by the colour alone. And beneath that clarity, a faint scattering of microscopic life moves with the current. These tiny organisms are so small that most people never think about them, yet they form the backbone of whatever life does exist here. Without them, the open sea wouldn't just be sparse, it would be silent at a level we rarely consider. The creatures that live in these vast waters don't thrive by speed or strength. They thrive by efficiency and patience. Where food is scarce, survival depends on moving slowly, feeding slowly, and conserving energy whenever possible. This means the animals here aren't racing through the water like you'd see near reefs. Instead, many of them drift along with the currents, letting the ocean itself carry them. Their bodies are often lightweight, streamlined, or even gelatinous, allowing them to stay afloat with minimal effort. These traits may seem unremarkable at first, but in an environment where energy must be guarded carefully, simplicity becomes an advantage. The open ocean also lacks the visual landmarks we're accustomed to. On land, even the emptiest desert has rocks, dunes, or shrubs. In a forest, trees dominate the landscape. But in the open ocean, there is no landscape the way we understand it. Everything is fluid. Everything moves, shifts, and changes its shape over time. Depth replaces distance, and layers of water replace layers of terrain. As you go deeper, light begins to disappear, and with it the ability to see more than a few faint shapes. The idea of space becomes harder to measure when there are no solid boundaries. Horizons don't change as you move. Distances blur into one another. You could travel for days and still look out at almost the exact same view you had before. That consistency is part of what makes these waters feel so different from other environments. You begin to realise how much we rely on variety to make sense of space. Trees, hills and buildings break up our view and anchor us. Even on a beach there are waves, shells, birds and people passing by. But out here you're left with one simple, continuous view that doesn't shift its personality. The ocean remains blue. The sky remains blue. The boundary between them stays clean and unbroken. And while this can feel calming, it can also feel disorienting if you're not used to such uniformity. The sailors who travelled across these waters generations ago struggled with that uniformity. They weren't explorers of the deep so much as travellers trying to reach distant lands, and the open ocean became the long, quiet stretch between familiar places. Their journals describe days when the sea looked so smooth and empty that it seemed like nothing lived beneath it at all. Fish followed the ships occasionally, but they were usually single wanderers, spaced far apart. Birds became rare. Seaweed almost never appeared. Without any visible signs of life, the travellers felt a strange combination of awe and uncertainty, as if the world had opened itself up so far that they no longer had anything to hold on to except the ship beneath their feet. Even today, with satellites and oceanographic data, we still feel that sense of wideness when looking at the central ocean gyres, the enormous rotating systems of currents that dominate the Pacific, Atlantic and Indian Oceans. These gyres cover nearly a third of the planet, forming some of the least productive marine environments on Earth. They aren't hostile or dangerous, they're simply quiet. Their water is some of the clearest in the world because so little grows in it. If you lowered a Secchi disc, the simple tool used to measure water clarity, you might see it sink until it reaches depths that would surprise you. Clarity, in this case, is a sign not of cleanliness but of scarcity. Sometimes the emptiness of these waters becomes visible in other ways. Plastic debris caught in the swirling currents collects in what people now refer to as garbage patches. These aren't solid islands of trash, as they're often portrayed, but more like large areas where floating plastic is more common than in surrounding waters. The fact that this material gathers so easily shows how little life there is to intercept it. In productive waters, things on the surface become caught in seaweed, eaten by marine animals or washed ashore. But in oceanic deserts, debris drifts for years because so few living things interact with it. It's another reminder that emptiness doesn't mean nothing is happening. It means the processes we expect from busier ecosystems are moving at a much slower pace. Travelling through these waters feels less like crossing a world filled with activity, and more like drifting through a space where everything has learned to be economical. You begin to notice how many creatures rely on strategies built on patience. Some fish migrate through these regions only briefly, using deep currents as highways. Some predators move through slowly, waiting for the rare moment when prey drifts close enough to justify a burst of speed. Even the smallest organisms grow at measured rates, using whatever nutrients they can find before the current carries them somewhere slightly more favourable or slightly more barren. And while you take in this landscape of subtlety and stillness, you may start to understand why some scientists call these areas the lungs of the ocean. Not because they teem with life, but because water circulates through them on long, slow journeys that influence global temperatures, carbon storage, and climate patterns. The emptiest waters are not unnecessary or forgotten. They are the quiet spaces between louder ones, helping the planet regulate itself in ways that aren't always visible but are always ongoing. If you were floating here at dusk, the light would soften across the surface in a way that makes the ocean look even larger. The sun wouldn't set behind mountains or buildings. It would simply descend into water, giving the impression that day is being absorbed rather than ending. Birds wouldn't gather overhead. Waves wouldn't crash. Instead, the horizon would shift colour slowly, until the world around you settled into a muted glow. In that simplicity, the idea of scale becomes clearer. You're a single observer surrounded by a planet-sized stretch of water that doesn't ask anything from you. It just continues, the same way it has for millions of years. And as the evening deepens, you might notice that the ocean's silence isn't really silence. It's more like an absence of competing sounds. There's the steady movement of water, the occasional creak of a boat or the distant call of a bird that wandered farther from shore than usual. There are subtle cues that the world is still active, just not loudly. The creatures that spend their lives here often move quietly, some rising from deeper layers at night to feed before sinking again when the sun returns. Many of them are transparent or lightly coloured to blend with the water around them. They aren't built to stand out, they're built to disappear until needed. By now, the sense of the ocean's vast middle becomes easier to grasp. It's not empty because nothing exists. It's empty because everything that exists has found ways to stretch limited resources over long distances and long lifespans. A single jelly-like organism trailing thin threads might drift for months before encountering something to eat. A solitary fish might travel tens of miles between meals. Even bacteria and microscopic life grow at rates that reflect the low-nutrient environment. Everything works on a slower schedule, one that doesn't fit our usual expectations but makes perfect sense here. As you continue drifting through this steady blue expanse, the emptiness becomes less something to question and more something to observe. You stop expecting dramatic scenes or sudden bursts of activity. Instead, you settle into the small details, the way light moves across the surface, the faint motion of something drifting just below, the long gentle rise and fall of the water. These things become enough to define the environment. They fill the space without overwhelming it, and gradually, almost without realizing it, you begin to feel how these waters set the stage for the kinds of life that manage to persist here, the ones that have shaped themselves around scarcity rather than abundance. Their stories soften the quiet, offering glimpses into how survival works in an environment where nearly everything is spread thin. As we continue forward, those stories become clearer, each one adding depth to the open water and revealing the subtle ways life adapts when the world around it offers very little. When people first hear that the largest stretches of the ocean hold the least life, it can sound backwards, almost like someone has mixed up their definitions. How can an environment that covers most of the planet, with sunlight shining on it day after day, be so poor in the very things that support living creatures? It feels counterintuitive, especially when we're used to thinking that bigger areas should offer more opportunities. But the ocean has its own patterns, and once you begin to understand how those patterns work, the idea that these vast blue regions are sparse starts to make more sense. They aren't empty because of harsh conditions or dramatic forces. They're empty because of how the building blocks of life move, settle, and spread through the sea. If you stand near a coast and look out at the water, you might see the ocean as one continuous surface, the same from shoreline to horizon. But beneath that surface, the chemistry changes in ways that matter far more than most people realize. Along the coasts, rivers carry nutrients from land into the sea. These nutrients, nitrogen, phosphorus, iron, and trace minerals, become the fuel for microscopic organisms that form the base of the marine food web. When these organisms, usually phytoplankton, thrive, they support zooplankton, fish, seabirds, and everything that depends on that cascade of energy. That's why coastal waters tend to look greener than the open ocean. The green tint comes from chlorophyll inside the tiny photosynthetic organisms multiplying rapidly. Life gathers where nourishment is plentiful, the same way plants cluster around water in a dry landscape. But once you move away from the coast, you enter a realm where the sea begins to lose that nutrient supply. The rivers no longer reach you, the seabed drops far below, and the water becomes clearer because so little grows in it. The sunlight is still present, and from the surface everything looks as inviting as before, but the ocean here is missing the essential ingredients for productivity. Without nutrients near the surface, phytoplankton struggle to grow, and without them, everything that depends on that first layer faces scarcity. And because these central ocean regions are so enormous, the effect becomes more noticeable. It's not that something is wrong, it's simply the way the ocean organises itself. A helpful way to imagine this is to picture the ocean as a moving conveyor system. Currents push water around the planet in long, slow loops. In certain places, especially near the equator and along western coasts, deeper water rises to the surface carrying nutrients with it. But in the large rotating systems found in the middle of the ocean, the opposite occurs. Water is drawn downward rather than upward. This downward movement traps nutrients far below the sunlit zone, leaving the surface layer clean but poor in the raw materials needed for growth. Sunlight alone can't create life. Something has to use that light to make energy, and that something needs nutrients. This is where the paradox begins to show itself. The oceanic deserts receive abundant sunlight, the same sunlight that fuels rich coastal regions and bustling coral reefs, but they lack the nutrients that allow that sunlight to be converted into biological energy. These waters are like vast, bright landscapes with empty shelves. There is plenty of illumination, but not enough material to build anything with it. The creatures that live here must adapt to a life where food arrives slowly, often carried in by drifting particles or by occasional mixing events. Many organisms depend on consuming things far smaller than they are, because the small things are the few that consistently appear. The word desert in this context isn't meant to imply harshness or dryness. It's meant to describe low productivity the same way we do on land. A desert on land doesn't lack sunlight, it lacks water. An oceanic desert doesn't lack water, it lacks nutrients. And yet, just like on land, the life that does manage to survive here becomes uniquely suited to doing more with less. If you've ever been in a place where food options were limited, and you had to stretch what you had, you might understand a small part of what these organisms face. They operate on the smallest margins, taking advantage of any moment when conditions become slightly more favourable. Some species grow slowly because they cannot afford fast growth in such a lean environment. Others drift through the water endlessly, waiting for the next molecule of nitrogen or the next fragment of sinking organic matter. Their entire existence revolves around making the most of rare opportunities. It might be tempting to assume that these waters are biologically unimportant, but the truth is that they cover such a large portion of the planet that even low productivity adds up to something significant. The tiny organisms living here contribute to global oxygen production, carbon cycling, and climate regulation. Their lives affect the chemistry of the entire planet, even though each individual cell may survive on almost nothing. The paradox becomes even clearer when you realise that these nutrient-poor waters often look the most inviting from above. If you've ever seen photographs of the open ocean from satellites, you might notice that the clearest blue regions are usually the least biologically productive. The clarity, which seems beautiful and pure, is the result of very few organisms absorbing or scattering the light. It's similar to how a glass of pure water looks clearer than a glass of water filled with algae. The beauty of the blue surface hides the scarcity beneath. Divers who enter these waters sometimes remark on how startlingly blue everything looks below the surface. Without plankton to cloud the water, light penetrates deeply, giving the illusion of an endless transparent world. But that clarity is also a quiet reminder that life hasn't filled the space the way it does elsewhere. If you were drifting in these waters and looked around, you might see a single translucent jelly drifting past, or a faint movement belonging to a small fish adapted to long stretches of emptiness. But you wouldn't see the busy, layered communities that thrive near richer environments. Here, the residents live far apart, as if each one occupies its own small world. To understand why this happens, it's helpful to look more closely at how nutrients move. When organisms in the surface waters die, or when waste sinks, those particles fall downward into the depths. Once they reach deeper layers, they're often consumed or broken down by bacteria, and the nutrients released during that process remain trapped below. Without a strong mechanism to bring them back upward, they stay locked away. Over millions of years, the nutrient profile of the ocean has settled into a pattern where the deepest waters hold the most nutrients, while the sunlit surface in the middle of the ocean holds the least. This separation of sunlight and nutrients is the core of the paradox. The two ingredients needed for productivity rarely meet in the middle of the sea. Where sunlight is strong, nutrients are low. Where nutrients are abundant, sunlight is weak. Only in regions where currents lift deeper waters upward do the two combine, creating bursts of life that form some of the richest ecosystems on Earth. The creatures living in nutrient-poor open waters do not fight this pattern. Instead, they adapt themselves to fit it. Some bacteria have evolved to use forms of nitrogen that other organisms cannot, giving them an advantage in environments where the usual sources are scarce. Some phytoplankton have developed specialized pigments that allow them to absorb light more efficiently. Some zooplankton move vertically through the water column, rising toward the surface to feed during certain times and retreating into deeper layers to reduce predation. These strategies reflect the slow, deliberate pace of survival that defines oceanic deserts. It's not just tiny organisms that feel the impact of this scarcity. Larger animals also navigate it, though their interactions with the environment look different. Certain species of tuna and sharks travel long distances through these waters, feeding opportunistically whenever they encounter suitable prey. They don't remain in these regions long enough to depend on them, but they pass through the same way a person might travel across an empty landscape, with occasional rest stops. Migratory species use these waters as corridors rather than destinations, and yet despite the sparseness, there's something compelling about the way life persists here. Instead of relying on abundance, it relies on efficiency. Instead of growing quickly, it grows steadily. Instead of building dense populations, it maintains low numbers that reflect the resources available. This balance creates an ecosystem that seems almost understated, but it is stable in its own way. It doesn't overflow, but it endures. One of the reasons scientists find these waters fascinating is that they reveal how little is required for life to continue, even on large scales. A single patch of phytoplankton drifting through the sunlit zone becomes food for a slightly larger organism, which becomes energy for another. These small exchanges ripple outward, creating subtle but important patterns in global cycles. Even in scarcity, the ocean participates in processes that influence the entire Earth. When you imagine these regions, it helps to picture the ocean as a place where the rules of productivity are reversed. Instead of crowds, you find solitude. Instead of bursts of activity, you find gentle pacing. Instead of dense food webs, you find thin lines connecting fewer participants. The open ocean isn't an empty auditorium. It's a sparsely attended gathering where each participant knows how much space is available and has adapted to fill precisely that amount. And yet the paradox deepens once you consider how much these regions matter to the rest of the world. Their size alone makes them important. Their circulation patterns influence climate. Their clarity affects heat absorption. Their microscopic residents help regulate the chemistry of the atmosphere. While they may not teem with life, they support the planet in other, quieter ways. As you continue drifting through this part of the story, the idea of scarcity becomes less about absence and more about adjustment. Life doesn't vanish because conditions are difficult. It reshapes itself around those conditions, and in the next part of this journey, the focus turns toward how invisible elements, especially sunlight and depth, create shifting layers that determine where life can linger and where it simply cannot take hold. When you think about landscapes, you probably picture things you can see and touch. Plains, hills, forests, anything with shape and texture. The ocean, at first glance, seems to lack that kind of structure. It appears to be a single, continuous space, without clear boundaries or features. But once you look beneath the surface, you discover that the sea has its own kind of terrain, built not from rock or soil, but from light. As the sun penetrates the water, it creates invisible layers that shape where life can exist, how it behaves, and how far it can drift before the darkness becomes too deep for survival. These layers form a kind of underwater world that we rarely think about because it doesn't reveal itself in the same way land does. Yet for countless organisms, these light-drawn zones are as real as any mountain or valley. The journey of sunlight into the ocean begins the moment its rays hit the surface. Some light is reflected immediately, bouncing off the shifting waves, but much of it enters the water and continues downward until the darkness absorbs it completely. That descent is not uniform. Water absorbs different wavelengths of light at different rates, which means the deeper you go, the more the colours change. Red disappears quickly, followed by orange, then yellow, until only blue remains. This is why the open ocean looks so intensely blue when viewed from above. It's not that the water is naturally coloured that way, but rather that blue wavelengths penetrate deeper than the others, making the surface appear filled with that single colour. This filtering effect is the first sign that light is creating boundaries beneath the surface. Creatures that rely on specific types of light gather in the upper layers, while those that prefer dimmer conditions remain below. It forms a gradient rather than a sharp division, but that gradient is powerful enough to determine what kinds of organisms can survive at different depths. The ocean divides itself into zones based on how much sunlight reaches them, and each zone supports its own community of life. The uppermost layer, where sunlight remains bright enough for photosynthesis, is where most of the ocean's productivity occurs. Even in nutrient-poor waters, this area supports the microscopic drifters that use sunlight to create energy. These organisms are so small that you cannot see them individually, but when they gather in large numbers, they influence the colour of the water, the clarity of the surface, and the flow of energy through the entire ecosystem. They form a thin but crucial layer that extends only as far as the sun can reach. The depth of this layer varies depending on water clarity. In coastal areas with murky water, sunlight may penetrate only a few dozen feet. But in the open ocean, where water is remarkably clear, light can reach much deeper. Even so, it still weakens quickly. By the time you're about 200 meters below the surface, photosynthesis becomes impossible because the sunlight is simply too dim. Everything beyond that depth must rely on food drifting down from above or on other strategies that don't depend on capturing light. This transition from light to darkness creates a boundary that is invisible from above, but deeply significant to the organisms that live within it. The bright upper layer feels like a sunlit field compared to the deeper zones that resemble a permanent twilight. For creatures living near the surface, the ability to capture or avoid light determines their daily patterns. Some organisms stay close to the surface to maximize their exposure, rising and falling with the movement of the sun. Others hide in deeper layers during the brightest part of the day to avoid predators, only coming up when the light softens enough to provide cover. Below the sunlit zone lies a region that many people imagine incorrectly. It isn't pure darkness, not at first. Instead, it is a place where light begins to fade gradually. Even at several hundred meters down, a faint blue glow can remain, just enough to outline shapes if you are able to see them with sensitive eyes. In this zone, called by scientists the twilight region, the absence of strong light forces organisms to adapt in different ways. Some develop large eyes to make the most of the faint illumination, while others produce their own light through chemical reactions. Bioluminescence becomes one of the main ways creatures communicate, attract prey, or defend themselves. Instead of relying on sunlight, these organisms create their own forms of visibility. Yet even here, light continues to change as you descend. Eventually, at around 1,000 meters, natural sunlight disappears entirely. Nothing from the surface can penetrate this far. Whatever lives in these deeper regions must exist without any contribution from the sun. Some organisms depend on the sinking remains of life from above, while others survive on chemical processes that do not require light at all. These zones may feel distant from the surface, but they are shaped by light in the sense that its absence determines what is possible. What makes this invisible layering so interesting is that it affects not just small organisms, but the entire structure of ocean life. Fish, jelly-like drifters, plankton, and even microscopic bacteria arrange themselves according to how much light they need or can tolerate. Everything competes differently here. For some, too much light is dangerous because predators can easily spot them. For others, too little light prevents them from finding food. These preferences and limitations create a kind of underwater distribution that looks random at first but follows consistent patterns. If you could glide downward through the water slowly enough to notice each change, you would feel the shift in illumination the same way you might feel the change from afternoon to dusk. At first, everything is bright. Then the brightness softens, the colours start to fade, the features of the surface become harder to recognise, and then a point comes where there is no light at all, only darkness stretching in every direction. It isn't frightening so much as unfamiliar, a kind of stillness that feels different from anything above. And yet, even before darkness takes over, the fading light creates patterns that act almost like barriers. For example, many species of phytoplankton cannot survive outside the top few dozen meters. They need direct sunlight to function, and once the light weakens beyond a certain point, they cannot generate the energy required to stay alive. They drift or sink into deeper layers where they are eventually consumed by bacteria or other organisms. In this way, the vertical movement of light influences the vertical movement of nutrients, even if the organisms are too small to control their own depth. Similarly, many predators in the open ocean time their behaviour around these light gradients. Some hunt only when the light is bright enough to reveal the silhouettes of prey. Others feed only in dim conditions to avoid being seen themselves. The rise and fall of light throughout the day creates a rhythm that controls everything from migration patterns to feeding cycles. It is an underwater version of day and night, felt even by organisms that never reach the surface. This lighting structure doesn't just affect individual species, it shapes entire communities. The upper layers become hubs for photosynthetic life and the animals that feed on it. The deeper layers become resting zones during daylight hours for creatures that venture upward only at night. The darkest layers become homes for species that have abandoned light altogether, relying instead on specialized adaptations that support survival in conditions where food is scarce. When you consider how much of the ocean falls into these deeper zones, it becomes clear that the majority of the planet's living space exists in environments where sunlight either fades or disappears entirely. Most of the ocean is not bright and colourful, it is dim, quiet, and sparsely populated. Yet it is filled with organisms that have shaped themselves around these lighting conditions, turning what appears to be a limitation into a way of life. The invisible landscapes created by light also determine how humans understand the ocean. When researchers lower instruments into the water, they often notice sudden shifts in readings. Once they pass the boundaries between light zone and dim zone, the temperature changes, the concentration of oxygen drops, and the density of organisms fluctuates. These subtle shifts tell scientists where different layers of activity begin and end. It's almost like reading a map, except the map is made from properties of light rather than physical structures. The boundary where sunlight becomes too weak for photosynthesis serves as a major dividing point in this invisible landscape. Above it, the ocean supports a thin but vital layer of life that influences global carbon cycles. Below it, organisms depend on the drifting remains from above, creating a downward flow of organic material that fuels deep communities. This movement of sinking particles, often called marine snow, connects the surface world with the depths, even though light cannot reach them. Each tiny particle becomes a small piece of nourishment for organisms waiting below. Marine snow might sound like a delicate process, but it is one of the key ways nutrients travel through the ocean. It includes everything that falls from the surface: dead plankton, waste from larger animals, fragments of jelly-like organisms, and tiny bits of organic matter. As this material sinks through the lightless regions, it supports life that would otherwise struggle to survive. In a sense, the lack of light creates a reliance on the surface, even if the creatures living below never see it. Sometimes, though, the layers created by light interact with currents and weather in ways that temporarily change the structure of the ocean. Mixing events can bring deeper nutrient-rich waters into the sunlit zone, causing brief periods of increased productivity. These events may last only days, but they reshape the distribution of organisms, leading to bursts of activity that ripple outward. Even in oceanic deserts, such events create temporary blooms of life, like a brief rush of growth in an otherwise quiet landscape. The deeper you travel in this invisible terrain, the more the absence of light becomes a defining feature. Beyond a certain point, the water is not just dim, it is completely dark. And yet, even here, organisms have found ways to survive. Many produce their own light, creating small points of illumination that move through the water like drifting stars. These lights are used for communication, camouflage, attraction, or defense. They are controlled responses to the lack of sunlight, allowing creatures to shape their environment in subtle ways. If you could pause in this total darkness and wait, you might begin to see faint glimmers appearing around you. They wouldn't light up the surroundings in the way sunlight does, but they would hint at the presence of life moving through the blackness. These glimmers, scattered across great distances, represent another kind of invisible landscape, one defined not by sunlight but by bioluminescence. Here, each light is both a tool and a message, revealing how creatures adapt to an environment where natural illumination never reaches. Even though these deeper regions are far removed from the surface, they still depend indirectly on the light patterns above. The sinking organic matter that supports them originates from the sunlit zone. The rise and fall of organisms aligning their movements with light cycles determines when and how much food reaches the depths. In this sense, light structures the entire vertical flow of energy, even in places where it never shines. Understanding these invisible landscapes provides insight into why the open ocean has such distinct communities. Light creates boundaries without walls, guiding where organisms can live, feed, and drift. It divides the ocean into functional layers that interact in complex ways, each one influencing the others. The open ocean isn't a featureless space, it is shaped by gradients rather than edges, and those gradients determine everything from biomass to behaviour. As you continue imagining this descent through light and darkness, the idea of the ocean as a single continuous environment begins to shift. It becomes clearer that these invisible landscapes play a role just as important as mountains or plains do on land. They create structure where none seems to exist. They determine movement where direction might otherwise be arbitrary, and they reveal how life adapts to constraints that seem subtle but carry profound consequences. And as the story continues, these layers of light help explain how the drifters, those tiny organisms that float through the ocean with no ability to swim against currents, navigate an environment where they depend almost entirely on what these invisible boundaries allow them to reach. If you picture the ocean's residents, you might first imagine large animals moving efficiently through the water, whales rising for air, sharks cruising in long arcs, fish weaving through schools. But most of the ocean's life, especially in its vast empty regions, doesn't move with purpose or strength at all. Instead, it drifts. It drifts because it has no choice. The creatures that make up plankton, the drifters, live in a world where the water decides their direction, their speed, and sometimes even their fate. They are not weak in the sense of being fragile. They are adapted to a life that depends on floating rather than swimming, surviving rather than controlling, and using what the ocean provides rather than shaping their own path. Their existence is quieter than that of larger animals, but it's also more fundamental. Without them, the sea would not operate the way it does. The word plankton might sound like it describes a single type of organism, but it actually refers to a lifestyle rather than a species group. Anything that drifts with the currents, unable to swim strongly enough to choose its direction, is considered plankton. This includes microscopic algae, tiny animals, larvae of much larger creatures, and even some jelly-like organisms that grow surprisingly large, yet still qualify because they cannot fight the flow of water. The range of forms and functions within plankton is enormous, and despite their small size or simple shape, they play roles that influence everything from food webs to climate patterns. At the heart of this drifting community are the smallest drifters, the photosynthetic ones that use sunlight to convert nutrients into energy. These organisms form what might be considered the ocean's version of grasslands. They are the primary producers, the starting point for any food that travels through the marine ecosystem. Even in the nutrient-poor waters of oceanic deserts, they persist in numbers that, though limited, remain essential. They harness the sunlight that filters into the upper layers and convert it into energy that other organisms can eventually consume. Without this thin layer of drifting life, even the larger animals that occasionally pass through would not be able to survive. If you were to scoop a bucket of open ocean water and examine it under a microscope, you'd see an entire universe of tiny structures moving gently in the water. Some would be shaped like spheres, some like chains, some like twisted ribbons. Their sizes would vary from a few micrometers to larger forms that can almost be seen with the naked eye. They drift together not because they intend to, but because the water groups them. Currents, wind, waves, and turbulence determine their patterns, bringing them into contact with one another or scattering them across miles of water. These tiny organisms do not seem impressive at first glance, but they have evolved remarkable adaptations to survive in an environment where food is scarce and competition is constant. Some have elaborate shapes that increase their surface area, helping them float more easily in the water column. Others store nutrients when they are available, allowing them to survive long periods when resources are sparse. Some form protective coverings, while others rely on rapid reproduction when conditions briefly improve. Each adaptation reflects a long history of living in an environment where drifting is not a drawback, but a requirement. The drifters also form the foundation for life that cannot create its own energy. Zooplankton, tiny animals that drift just as helplessly, depend on consuming phytoplankton or other small particles that drift alongside them. These zooplankton include a wide variety of organisms, from tiny crustaceans that resemble specks under a microscope, to transparent gelatinous creatures that stretch and contract with each movement. Many of them behave in ways that reveal how much their world is shaped by light and currents. At night, countless zooplankton rise toward the surface to feed when the darkness provides cover from predators. When the sun returns, they sink again into deeper layers, where the dim light offers greater safety. This movement, known as DL vertical migration, is considered one of the largest mass movements of life on Earth, even though most of the participants are too small to be seen without special equipment. This daily rise and fall influences more than just the lives of the drifters themselves. Their movement transports carbon, nutrients and energy through the water column in a continuous cycle. As they feed at the surface and then retreat into deeper layers, they carry the products of photosynthesis downward, effectively transferring material from the sunlit zone to regions where light cannot reach. This vertical exchange supports life in areas that otherwise lack direct access to the energy created by phytoplankton. It becomes one of the many quiet systems that hold the ocean together. Some of the drifters live short lives measured in days or weeks, while others exist for months, their fate determined by how the water moves. They may drift hundreds of miles over their lifetime, carried through zones with different temperatures, salinities, and nutrient levels. Each shift alters their behavior subtly. A patch of water with more nutrients may allow them to grow and reproduce more quickly, while a nutrient-poor patch forces them to slow down. Because they cannot choose their direction, their survival depends on matching their own needs to the environment they find themselves in. It is a delicate balance, but one that has proved successful for millions of years. One of the most striking things about plankton is how much diversity exists among creatures that share the same drifting lifestyle. Some phytoplankton species are simple in structure, with little more than a cell wall and the machinery needed for photosynthesis. Others have intricate shapes made from silica or calcium carbonate, forming tiny structures that look almost like sculptures when viewed closely. These shapes are not decorative. They help regulate buoyancy, protect against predators, or increase efficiency in absorbing light. Even within the simplest organisms, the ocean has found countless ways to fine-tune survival. Zooplankton shows similar variety. Some are shaped like tiny shrimp, constantly flicking their appendages to stay afloat. Others resemble globes of jelly that pulsate softly as they drift. Some have transparent bodies that make them almost invisible to predators. Others produce faint glows of bioluminescence when they are disturbed, a response that can confuse or startle anything that tries to eat them. Despite their differences, they share the same dependence on drifting. Their bodies are adapted to floating rather than swimming, and their movements are usually small adjustments rather than deliberate travel. It can be difficult to appreciate the importance of these drifters because they are so small and their actions are so subtle. Yet they influence nearly every part of the ocean's functioning. They produce oxygen, regulate carbon dioxide, support food webs, and shape nutrient cycles. Even creatures much larger than they are depend on them, often indirectly. A large fish might feed on smaller fish that have fed on zooplankton, that in turn consumed phytoplankton. The energy pathway begins with organisms far too small to see, but essential all the same. The idea of drifting may sound passive, but for plankton it is a highly active way of life. Their survival depends on responding quickly to changes in their environment. If nutrients suddenly increase due to a mixing event or passing current, phytoplankton may grow rapidly, forming blooms that temporarily transform entire regions of the ocean. These blooms can attract zooplankton, which then attract fish, creating a temporary chain of abundance in a place that usually holds much less. The bloom eventually fades, and the drifters return to their usual sparse numbers, but the temporary surge supports organisms that rely on these brief moments of plenty. Not all drifters depend on photosynthesis or feeding on phytoplankton. Some bacteria drift through the water column, breaking down organic material and recycling nutrients. Their work may seem invisible, but without it, the ocean would quickly become overwhelmed by the remains of organisms that die or release waste. These bacteria help maintain the balance of the ecosystem by ensuring that nutrients do not remain locked in unusable forms. They break down marine snow as it falls through the water column, releasing energy that other organisms can use. Even in the emptiest waters, these microscopic recyclers persist, doing work that allows life at all depths to continue. Because the drifters form the basis for so many processes, their abundance or scarcity has far-reaching effects. In nutrient-rich regions, phytoplankton can multiply rapidly, supporting thriving ecosystems. In the barren open ocean gyres, their numbers are far lower but still essential. They may grow more slowly or reproduce less frequently, but they remain the starting point of the food web. Their constant presence, even in small quantities, allows zooplankton to survive, which in turn supports larger organisms that pass through. The drifting lifestyle also explains why plankton are so widely distributed. Because they cannot control their own movement, they are carried across entire ocean basins. A phytoplankton cell in the middle of the Pacific may have descended from ancestors that drifted in from far away, brought by currents that move slowly but persistently. This movement ensures genetic diversity, spreads species across vast distances, and prevents any single area from becoming completely isolated. Even in regions where life is sparse, the ocean continues to circulate organisms, spreading them across thousands of miles. Despite their importance, plankton are often overlooked when people think about ocean life. They are too small to see from the surface and too numerous to isolate as individuals. But without understanding them, it becomes difficult to understand the broader patterns of ocean life. They provide the first step in an energy chain that stretches upward through every layer of the ecosystem. They reveal how the ocean responds to environmental changes. They show how life persists in conditions that might otherwise seem too empty to support anything at all. If you imagine drifting alongside these tiny organisms, you might begin to appreciate how different their world is from ours. You would feel the gentle movement of water carrying you through layers of light and shadow. You would experience long stretches of time where little changed, punctuated by brief moments of abundance when nutrients suddenly appeared. You might find yourself floating among countless other organisms, each one doing its part to support a system far larger than itself. And you would realize that drifting is not aimlessness. It is a way of being in tune with the rhythm of the ocean. Even though plankton cannot choose their direction, they shape their environment through their behavior. They create blooms that alter water chemistry. They become food for larger organisms. They help regulate climate processes by absorbing carbon. They drift, but their drifting has meaning, both for themselves and for the countless other creatures that depend on them. As this slow journey continues, the focus naturally shifts toward those creatures that do more than simply drift. Some must hunt in a world where food is scarce and movement consumes precious energy. They navigate the same empty waters as the drifters, but with different challenges and different strategies, revealing yet another layer of how life adapts to the quietest parts of the sea. When you imagine a hunter, whether on land or in the sea, you probably picture something swift, muscular, and constantly in motion. Something with sharp senses and fast reflexes, always ready to strike at the first hint of prey. In many environments that image makes sense. Predators often need speed, power, and precision to catch their food. But in the emptiest parts of the ocean, those qualities would be more burden than advantage. Here, where life is spread thinly across thousands of miles, and prey may appear only occasionally, the creatures that survive are not built for sprinting or chasing. They're built for scarcity. They succeed not by overpowering their world, but by conserving every bit of energy, waiting with patience that seems almost unimaginable, and using strategies that allow them to thrive when meals are more rare than abundant. The open ocean, especially in its quietest central regions, doesn't offer the dense schools of fish or clusters of invertebrates found near coasts or reefs. Instead, it offers long expanses where even small patches of plankton are separated by large stretches of water. Any creature hoping to hunt here must find a way to make the search worthwhile. Moving constantly would burn more energy than the prey could replace, but waiting passively means risking starvation. Predators here navigate a delicate balance between motion and stillness, action and restraint. One of the most familiar hunters in these waters is the slender, wandering fish known as the lancet fish. Its long ribbon-like body allows it to glide through the water with minimal effort. Its dorsal fin rises like a curved blade, and its mouth holds sharp teeth that look fierce enough to suggest a life of constant feeding. But the reality is that lancet fish are slow, cautious hunters. They spend much of their time drifting, conserving energy, waiting for the right moment to lunge at whatever happens to drift past. They feed on small fish, squid, crustaceans, and even jelly-like organisms, taking advantage of whatever the ocean provides. Their bodies reflect a lifestyle where opportunities are unpredictable, and survival depends as much on restraint as on aggression. Another resident of these sparse waters is the oceanic white-tip shark, a species known historically for its wide-ranging movement and opportunistic feeding. The white-tip does not patrol territories or chase prey in long bursts of speed. Instead, it cruises slowly through open water, using its broad fins to maintain buoyancy and glide effortlessly. This slow pace is not a sign of weakness, but of adaptation. In a place where food may be scarce for long periods, wasting energy on constant motion would be unsustainable. The white-tip is a patient traveller, exploring vast distances in the hope of encountering floating carcasses, schools of fish drawn to rare patches of productivity, or marine mammals resting near the surface. It has learned to take advantage of chance rather than rely on abundance. This kind of opportunistic hunting is common among creatures that live in oceanic deserts. Instead of focusing on specific prey, many of them are generalists. They eat whatever is available, even if it isn't ideal. When a whale dies at sea and begins to sink, it releases a cloud of nutrients that draws predators and scavengers from miles around. Sharks, fish, and even deep water organisms rush to take advantage of the unexpected bounty. These events are rare, but in a nutrient-poor environment, even one such occurrence can sustain multiple species for a significant period. Hunters here are experts at recognizing opportunities when they arise, responding quickly but conserving energy the rest of the time. Another creature adapted to this lifestyle is the long, thread-like siphonophore. Although it may look like a single organism, a siphonophore is actually a colony made of specialized units, each performing a different function. Some parts of the colony float, others capture prey, others digest food, and others help with reproduction. Siphonophores can reach astonishing lengths, some over 30 meters, yet remain nearly invisible in the water. They extend delicate, stinging tentacles that drift like thin threads, capturing any small organism that happens to make contact. They do not swim after prey. They simply extend their reach and wait, relying on the enormous size of their colony to increase the probability of encountering food. Their hunting strategy is passive but effective, especially when prey is scarce. The concept of conserving energy becomes even clearer when you look at gelatinous predators such as certain types of jelly-like animals and ctenophores. These creatures have bodies composed mostly of water, requiring minimal energy to maintain. Because they weigh so little and offer little resistance to the movement of currents, they can drift for miles without effort. Their feeding tactics rely on slow, steady movements and sticky tentacles, or cilia, that capture prey on contact. These animals do not need to chase anything. They exist in a world where patience and persistence often outweigh speed or intelligence. One of the most intriguing hunters in the open ocean is the daggertooth fish. Despite its intimidating name, the daggertooth does not expend much energy in pursuit of prey. It possesses long, needle-like teeth designed to impale prey quickly, but the fish itself remains slow-moving. It hides in deeper layers during the day, rising toward the surface at night as part of the nightly vertical migration that so many creatures in the open ocean participate in. This migration allows the daggertooth to follow the zooplankton and smaller fish that also rise at night to feed on phytoplankton. In this way, the daggertooth leverages the movements of other organisms rather than expending unnecessary energy creating its own opportunities. Another predator worth examining is the giant salp chain. Salps themselves are not hunters in the traditional sense. They are gelatinous creatures that filter microscopic food from the water. But when populations of salps grow and link together into long chains, they form drifting filters that can remove large amounts of plankton from the water column. Their collective feeding can create temporary zones of scarcity for other animals, altering the food landscape for miles around. In this sense, the salps become hunters of opportunity, not actively pursuing prey, but consuming what they encounter in enormous numbers when conditions are right. Their strategy is to be abundant when nutrients briefly appear and then diminish again as the supply drops. Some hunters in the open ocean take advantage of the fact that the surface can gather floating debris, drifting seaweed, or even small organisms carried by wind and currents. The ocean's surface acts like a natural collection point, and predators such as mahi-mahi or certain tuna species patrol these floating objects, waiting for smaller creatures that gather beneath them. These predators move more quickly than others in these waters, but they still conserve energy by focusing their efforts on small, predictable hotspots of life. Instead of roaming aimlessly, they target specific features that tend to concentrate prey. In contrast, creatures like the deep-living dragonfish use a different tactic. Though they inhabit darker, colder layers of the ocean, they still qualify as hunters of scarcity, because they depend on drifting prey and occasional encounters. Many dragonfish species possess bioluminescent lures that attract small animals. These lures glow faintly in the darkness, drawing attention from organisms searching for food. When something approaches, the dragonfish snaps its jaws with a speed and precision that seems surprising given how still it remains most of the time. These fish embody the idea of conserving energy until the critical moment arrives. Survival in the open ocean requires a combination of strategies that depend heavily on adaptations to low resource availability. Some species store energy in the form of fats or oils, enabling them to go long periods without feeding. Others have reduced muscle mass or lightweight skeletons that make movement more efficient. Still others have sensory adaptations that allow them to detect prey from greater distances. These features reflect the constant pressure to make the most out of very little. Another interesting group to consider is the flying fish. While not hunters themselves, they are prey for many species in the open ocean. Their ability to leap out of the water and glide above the surface offers them a temporary escape from predators below. This unusual adaptation benefits not just the flying fish, but also the predators that must adjust their tactics to account for prey capable of sudden aerial movement. Here, scarcity shapes behaviour for both sides: prey that must evade becoming someone's rare meal, and predators that must anticipate escape attempts. Large predators like marlin or sailfish also travel through open ocean environments, using bursts of speed to catch prey when they find it. These animals cannot afford to sprint constantly. Instead, they rely on cruising speeds that allow them to conserve energy. When they do accelerate to catch a fish or squid, they do so with precision, often using short bursts that last only seconds. Their strategies reveal how even larger animals must adapt to these sparse regions. Their speed is valuable, but only when used sparingly. One might assume that the most efficient hunters in the open ocean would be those with the highest intelligence or sensory abilities. But often the most successful ones are the simplest. They drift, wait, extend tentacles, or glow faintly in the darkness. Complexity is not always advantageous in a world where food is rare. Simplicity often offers the best chance for long-term survival. When you consider how these creatures navigate their sparse environment, it becomes clear that their lives revolve around rhythms shaped by light, currents, and the availability of prey. They may drift for days or weeks without feeding, then suddenly encounter a patch rich in zooplankton or a small school of fish. These moments become critical. A successful feeding event can sustain an organism for long periods, allowing it to continue conserving energy until the next opportunity appears. If you were drifting through the water alongside these hunters, you would notice how unhurried they seem. They do not dart around like reef fish or chase prey with the urgency of coastal predators. Instead, they move slowly and deliberately, conserving energy and waiting for the right moment. Their environment shapes their behaviour in ways that emphasise endurance over excitement. In this world of scarcity, every adaptation becomes significant. A slight improvement in buoyancy can mean the difference between conserving energy and wasting it. A faint glow can attract prey without alerting predators. A drifting position can place an organism in the path of potential food. Everything is calibrated to the slow pace of an environment where resources come and go in unpredictable cycles. These hunters show how life persists even when opportunities are few. They reveal that survival doesn't always require speed or power. Sometimes persistence, patience, and an ability to make the most of whatever the world provides become the keys to endurance. Their existence adds another layer to the understanding of oceanic deserts, showing that scarcity doesn't prevent life. It simply reshapes it into forms that align with the conditions. And as the story continues, the focus begins to shift toward the rhythm that governs these creatures' lives. Not just the movement of prey and predators, but the careful use of time and energy that defines how organisms in the open ocean manage to continue surviving in waters where everything moves slowly and every moment must count. In the emptiest waters on Earth, the pace of life shifts in ways that feel almost unfamiliar compared to the speed and vividness we're used to seeing near coasts or coral reefs. Movement slows, choices narrow, time stretches. Energy becomes something that creatures measure with a precision we rarely think about, because every pulse of a muscle, every flick of a fin, every decision about whether to chase or wait comes with a cost. In an environment where food appears unpredictably and often in tiny amounts, even the simplest actions must be weighed against the risk of wasting energy that cannot easily be replaced. This creates a style of existence where slow motion isn't a luxury, it's a necessity. If you imagine drifting through these waters, you might notice that very little seems to happen at first. No sudden flashes of movement, no chaotic chases, no tight clusters of fish turning in unison. Instead, you see long periods where creatures simply hover, glide, or float. For many of them, stillness is the safest and most efficient state. Staying still means conserving calories. It means waiting for currents to bring food rather than wasting energy seeking it. It means surviving not by acting often, but by acting only when absolutely necessary. This slow pace begins at the smallest scale. The phytoplankton floating near the surface grow more slowly here than in richer waters, because nutrients are limited. In coastal areas, phytoplankton may double in number within a day. In the open ocean, the same process may take several days. This slow growth affects everything above it. Zooplankton that depend on these microscopic producers also grow more slowly, reproduce less frequently, and feed more cautiously. Their entire life cycle stretches out, sometimes taking far longer than their coastal relatives. Because zooplankton are the primary food source for many animals, including small fish, jelly-like organisms and larvae of larger species, this slower pace has a cascading effect. Creatures that feed on zooplankton must adapt to long periods with only trace amounts of food available. They cannot afford constant movement, so many of them evolve bodies that require minimal energy. Transparent tissues, gelatinous structures, and lightweight skeletons help reduce the metabolic cost of staying afloat or drifting through the water column. These strategies might seem simple, but they allow organisms to survive where more robust or muscular creatures could not. Take the example of the larvaceans, tiny animals that build delicate, house-like structures made of mucus to filter microscopic food from the water. These structures, though temporary, allow the larvaceans to gather enough particles to sustain themselves without needing to swim constantly. When the filter clogs, the animal simply abandons it and builds another, letting the old structure sink like a piece of marine snow. This approach saves energy while allowing the larvation to feed passively, relying on the movement of water rather than on costly searching. Many other organisms use similar passive feeding strategies. Ctenophores, sometimes called comb jellies, drift through the water with rows of tiny cilia that shimmer as they beat slowly. The cilia aren't used for speed. They are used for gentle movement that requires minimal force. The ctenophores extend sticky tentacles that capture prey when it happens to drift into reach. They don't chase anything. They simply wait, letting the ocean do the moving for them. Even fish that live in these waters may demonstrate a kind of cautious pacing that feels different from fish closer to shore. Instead of darting around, many species hover or swim with long, slow strokes of their fins. Their muscles are adapted for endurance rather than bursts of power. Some have reduced bone density or higher fat content to help them remain buoyant without constant motion. Many have large eyes to make the most of limited light, allowing them to detect faint movements that signal the presence of prey. Everything about their physiology reflects energy conservation as a guiding principle. A classic example of life in slow motion can be found in the deep scattering layers, zones of the ocean where countless small organisms gather during the night to feed near the surface, then descend during the day to avoid predators. This massive daily migration involves trillions of animals, making it one of the largest movements of life on the planet. Yet, despite the scale of the migration, each individual organism moves slowly. A small fish may ascend from several hundred meters down, but it does so gradually, conserving energy at every step. Even when this migration spans entire ocean basins, the pace remains controlled. Fast movement is rare, reserved only for moments of danger. Some species take slowness to an extreme. There are animals that drift for years before reaching maturity, feeding only occasionally. Certain deep-water shrimp may grow so slowly that their life cycles span decades. Even some jelly-like animals, which might appear fragile, endure long periods of near starvation by reducing their metabolic rate until conditions improve. These creatures are not just slow, they are controlled. Their pace matches the reliability of the environment, making sure that every calorie is used with intention. In nutrient-rich regions, an organism might afford to waste energy on unnecessary movements, or to grow quickly without worrying about where the next meal will come from. But here, a single mistake can cost too much. If a fish expends too much energy chasing prey that escapes, it may not have enough reserves to recover. If a jelly-like organism pulses too frequently, it may lose more calories than it can replenish. Everything becomes a calculation, even if that calculation is guided by instinct rather than thought. The environment itself reinforces this slow rhythm. Currents in the central ocean gyres move with a broad looping motion, creating a kind of gentle circular treadmill that carries organisms slowly across thousands of miles. Temperature shifts gradually, and oxygen levels change only at depth. There are few sudden events that disrupt these rhythms. As a result, creatures have evolved to match the predictability of the environment, shaping their internal processes to align with the pace of the water around them. Some species slow their metabolism so dramatically during food shortages that they enter states similar to dormancy. Their heart rates drop. Their movement ceases almost entirely. They survive on stored energy until conditions improve. This strategy is common among certain gelatinous organisms, some fish larvae, and even some deep-water crustaceans. Rather than struggle against scarcity, they pause themselves, waiting for the environment to offer another opportunity. Even predators known for their powerful bodies sometimes adapt to this slower style of living when they travel through oceanic deserts. Large sharks, such as blue sharks or silky sharks, glide with minimal fin movement, letting buoyancy and slow currents do the work for them. Their bodies are streamlined not just for speed, but for efficiency. They save their bursts of power for the rare moments when they encounter prey worth pursuing. In many cases, these bursts last only seconds, followed by long periods of steady drifting. Another example lies in the behaviour of squid found in the open ocean. Unlike coastal squid, which can be agile and energetic, the squid that inhabit these central waters often move more sparingly. They use jet propulsion only when absolutely necessary, preferring gentle fin movements that carry them along at low energy cost. Their bodies are built for floating, not sprinting, and they rely heavily on camouflage or transparency to avoid predators rather than escaping through fast motion. This slow motion existence becomes even more pronounced as you move deeper into the ocean. At depths where sunlight has faded to near darkness, many organisms adopt strategies that revolve around minimizing any expenditure of energy. Their metabolism slows to match the cold temperatures. Their muscles become less developed. Their movements become small and deliberate. Some fish in these depths may go days between meals, conserving energy through stillness and reduced muscle tone. Despite these adaptations, life in slow motion does not mean life without complexity. Many of these organisms show remarkable behaviours despite their energy constraints. Some migrate vertically with surprising precision, timing their movements to coincide with the presence of prey. Others use chemical signals to locate food sources in the water. Some produce faint glows to communicate or attract prey. Even though they move slowly, they interact with their environment in ways that reveal an awareness shaped by millions of years of selective pressure. Slow living also affects reproduction. many species produce fewer offspring than their coastal relatives because creating new life consumes significant energy. But the offspring that are produced often have strategies for surviving sparse conditions. Some hatch into larvae, capable of feeding on microscopic particles, allowing them to drift for long periods before finding enough food to grow. Others enter the water column during times of year when productivity is slightly higher, ensuring that they encounter at least some resources during their early development. One of the most fascinating aspects of life in slow motion is how it ties into the overall stability of these ecosystems. Because everything moves and grows slowly, the environment does not experience sudden booms and busts in population sizes. Instead, changes unfold gradually. If a particular species becomes more abundant due to a slight increase in nutrients, the effects ripple outward in measured steps. The system remains balanced, not through constant activity, but through the long-term pacing that scarcity enforces. In many ways, life here mirrors the ocean itself. The water moves steadily but calmly. The light fades gradually. The nutrients drift downward slowly, and the creatures follow these rhythms without resisting them. Rather than pushing against the limitations of the environment, life adapts by synchronizing with its pace. If you imagine floating somewhere within this vast blue space, watching creatures move with patience rather than urgency, you might begin to understand how different their existence is from the fast-moving scenes often shown in documentaries. There are no sudden bursts of colour or dynamic chases. There is no rush to claim territory or find mates. Everything unfolds at a pace dictated by the steady, reliable scarcity of the environment. The ocean does not hurry here, and neither do the organisms within it. This slow-motion world sets the stage for a transition into something else, an understanding of how creatures that do not remain in these waters year-round fit into the puzzle. Some animals visit these oceanic deserts only temporarily, travelling through them as part of larger migrations. Their presence adds motion and occasional bursts of activity to a place that otherwise feels timeless. And their movements reveal even more about how the emptiest parts of the sea fit into the broader patterns of life across the planet's waters. When you spend enough time imagining the emptiest parts of the ocean, it becomes easy to picture them as isolated worlds, places where only the slow, permanent residents drift through the water, with no real interruptions. But these quiet regions aren't entirely cut off from the rest of the sea. They are crossed by travellers, visitors that come and go depending on the season, the temperature, the currents, and food patterns unfolding thousands of miles away. These animals are not built for long-term life in scarcity, but they are built to move, across basins, across hemispheres, across entire oceanic systems. They pass through the thin blue silence as part of larger journeys that connect richer regions with quieter ones, carrying energy, nutrients, and activity into waters that otherwise remain calm. The creatures that move through these regions often appear and disappear with little pattern visible from the surface. They are not permanent residents, but temporary guests. Their movements are shaped by migrations that, in many cases, span distances almost difficult to comprehend. For them, the emptiest waters on Earth are neither destinations nor obstacles. They are corridors. They're the long stretches of open sea that must be crossed to reach feeding grounds, breeding areas, or environments where conditions align just right for a particular phase of life. And during these crossings, they bring with them a kind of motion that stands out sharply against the slow, measured pacing of the permanent residents. Consider the tuna species that roam the open ocean. Their bodies are shaped for continuous motion, with strong muscles, streamlined forms, and specialised systems that regulate their temperature. Tuna travel across ocean basins in long arcs, moving quickly when necessary, but also maintaining cruising speeds that let them cover vast distances with efficiency. They cannot stay in nutrient-poor waters for long because their energy demands too high. Instead, they skim through these regions, searching for patches of prey such as small fish or squid that temporarily gather around drifting debris or subtle temperature fronts. Their presence is fleeting, a momentary break in the stillness of the sea before they continue onward. Other visitors include marine mammals like pilot whales or certain species of dolphins that occasionally glide through oceanic deserts while following schools of fish or squid. These animals rely on more abundant prey that typically doesn't thrive in the sparse middle of the ocean, but sometimes small aggregations of food appear unexpectedly, brought by currents or linked to the slow rise and fall of deeper layers. When these small oases form, the visitors arrive, feed, rest, and then continue their journey toward waters that can sustain them more reliably. Their encounters with the emptier parts of the sea may be brief, but they leave an impression on the ecosystem that lasts longer than their stay. Some of the most recognisable ocean travellers are sea turtles, which make migrations that span entire ocean basins. Leatherbacks, for example, travel remarkable distances in search of jelly-like prey. They move slowly but steadily, covering thousands of miles over the course of their journeys. While leatherbacks feed primarily in more productive waters, they often pass through oceanic deserts on their way to and from breeding areas. Their size and endurance allow them to cross these food-poor regions, and their movements reflect a deep connection between the scattered productive zones of the ocean. Each passage becomes part of a cycle that influences not only their own lives, but also the flow of nutrients across ecosystems. Wandering albatrosses and other seabirds also cross these empty waters regularly, sometimes making journeys that circle the globe. Despite spending most of their lives far from land, these birds rarely rely on the open ocean as a feeding ground. Instead, they use the vast emptiness as a travel route between areas rich in squid or fish. Their wings carry them across enormous distances with minimal energy use, allowing them to glide over the water for hours or even days without flapping. When they pass over oceanic deserts, their presence is subtle. A shadow moving across the surface, a faint silhouette against the sky. But their movement reminds us that even the emptiest waters are connected to places overflowing with life. Some fish, like the ocean sunfish, also drift through these waters as part of long wandering journeys. Sunfish feed on gelatinous prey, which can be found in small amounts even in nutrient-poor regions. They often travel long distances between feeding sites, remaining close to the surface where sunlight warms the water. Their large size and slow movements make them seem out of place in such empty surroundings, but they are remarkably adaptable. Their journeys take them through the richest and the quietest parts of the ocean, making them a bridge between two very different worlds. Migratory sharks, such as the blue shark, also use the open ocean as a travel path. Blue sharks often cover thousands of miles over the course of a year, moving between cold and warm waters depending on the season. They feed opportunistically on squid and fish that gather in small pockets of productivity, but their bodies are designed to endure long stretches with little food. Their streamlined shapes reduce the energy needed for movement, and they glide through currents rather than fighting them. This efficiency allows them to pass through oceanic deserts without exhausting themselves, making them one of the most successful travellers in these waters. The behaviour of these visitors reveals something important about the structure of the ocean. Even though certain regions may be poor in nutrients, they are still essential components of global migration routes. Many species depend on long-distance travel to survive, and the open ocean provides the space for these movements. Without these vast corridors, creatures that rely on far-flung habitats would struggle to complete essential stages of their lives. The oceanic deserts, despite being sparse, offer stability. The conditions here do not change rapidly. The temperature remains relatively predictable. The currents move slowly but consistently. For migratory creatures, this predictability is almost as valuable as food. The twilight zone, a region that stretches down from the edge of the sunlit layer into dim blue depths, also plays a role in these migrations. Many animals, including fish, squid, and larger predators, move vertically through this region as part of daily cycles. Creatures from richer waters sometimes extend their movements into the twilight when they travel through oceanic deserts. The dim light allows them to avoid predators or to search for deeper prey. The twilight becomes a kind of highway, a protected route beneath the surface where animals can move with less risk of being detected. Some species that normally inhabit coastal or productive waters may enter oceanic deserts during their larval stages. Ocean currents carry eggs and larvae far from their origin points, sometimes delivering them into these quiet central regions. Not all larvae survive the journey, but some drift long enough to eventually reach more favourable conditions. These drifting young form a subtle part of the open ocean's ecosystem, contributing to the slow, continuous distribution of life across vast distances. Their presence adds variability to the otherwise sparse biological landscape, offering feeding opportunities for small predators adapted to take advantage of whatever drifts into reach. Even creatures that rely on rich feeding grounds must acknowledge the role of the open ocean in shaping their movements. For example, certain species of whales migrate between polar regions and tropical breeding grounds. During these journeys, they pass through large expanses of nutrient-poor water. They do not feed much in these regions, but they conserve energy by adjusting their pace and relying on stored fat. As they move through the quiet blue, their bodies cast large shadows across the surface, hinting at the temporary presence of giants in a place normally defined by small, slow-moving residents. Visitors from full seas do not remain long enough to alter the structure of oceanic deserts permanently, but they create brief moments where the quiet becomes less quiet. When a school of tuna passes through, the water below them briefly flickers with movement. When a group of dolphins glides by, the surface breaks with arcs of motion. When an albatross swoops low, the air gains a hint of activity. These moments do not last, but they remind us that even the calmest waters are part of a larger system filled with travel, migration, and cycles that span enormous distances. What brings these creatures into such empty waters varies. Sometimes it is temperature, sometimes it is breeding, sometimes it is a current that pushes them farther offshore than usual, and sometimes it's simply part of their normal range, a reminder that their world is not divided into neat zones but stretches across entire oceans. The same creature might spend 1 month feeding in nutrient-rich waters, the next travelling through a nutrient-poor region, and the next arriving in a completely different environment. Their lives unfold across gradients rather than boundaries. The silent expanses of the open ocean also shape how these visitors interact with the animals that live here permanently. Predators travelling through may attempt to feed on resident species like slower-moving fish or gelatinous organisms, but just as often, the visiting predators encounter only sparse prey and continue onward. The residents, adapted to scarcity, may avoid these brief visitors through camouflage, vertical migration, or simply by drifting away. The interactions are fleeting, shaped by the fact that neither group is fully reliant on the other. What makes these travels especially interesting is that many of them occur in ways that aren't visible to us. From the surface, the ocean might look empty, even when hundreds of animals are passing through below. Migratory species do not typically announce their presence. They move with efficiency and purpose, leaving almost no trace behind. Their journeys become part of the ocean's quiet rhythms, noticeable only to those who study movement patterns or track animals through satellite tags. If you were drifting in these waters, watching one of these temporary visitors glide past, the moment might feel like spotting a traveller on a long empty highway, someone passing through on their way to somewhere else. They don't stop for long, they don't reshape the environment, but their passage adds a sense of connection, a reminder that even the loneliest places are woven into the wider movement of life. These twilight movers, whether they swim near the surface or slip through deeper layers, show that the emptiest parts of the ocean are far from isolated. They are roots, lungs, bridges, and long-distance corridors. They remind us that the ocean is one continuous system, not a collection of separate worlds. And as the story continues, the focus begins to shift toward what happens when something breaks the stillness in an entirely different way. Not by movement of animals, but by the rare appearance of floating structures or drifting habitats that concentrate life temporarily in places where scarcity usually reigns. When you imagine the most barren regions of the ocean, it's easy to picture a place where resources are spread so thin that nothing ever breaks the pattern. No sudden crowds, no bursts of activity, no unexpected gatherings of life. But even in these wide, open stretches, the sea has a way of surprising itself. Occasionally something drifts into view that changes the rhythm of an otherwise predictable environment. These objects, sometimes small enough to go unnoticed, and sometimes large enough to resemble floating patches of landscape, become temporary centres of activity. For a moment, or a few days, or even a few months, they turn an oceanic desert into a place that resembles a tiny oasis. They act like mirages in water, not illusions, but sudden fleeting breakpoints in the emptiness that gather life the way an island gathers birds. These floating islands come in many forms. Some are natural, like rafts of seaweed torn from coastal beds, or pieces of driftwood carried far offshore by storms, or even dead animals whose bodies float at the surface before eventually sinking. Others are accidental products of human presence, buoys, bits of fishing equipment, fragments of plastic, or any object buoyant enough to persist in the surface waters. Whatever their origin, these floating structures share one thing in common. They provide something the open ocean rarely offers. They offer attachment points, shade, shelter, or a place where food collects. And those small advantages are enough to draw life from miles around. In nutrient-poor waters, nothing stays in one place for long. Currents carry everything steadily along, redistributing small particles and organisms in patterns that are mostly diffuse and unpredictable. But when a floating object appears, even something as small as a branch, it disrupts the normal flow. The water slows slightly around it. Tiny organisms drifting near the surface gather in its wake. Zooplankton cluster in the small patches of shade it creates. Small fish, especially juveniles, find temporary protection beneath it. For these creatures, the object becomes a refuge, a landmark in an environment where landmarks don't exist. Seaweed rafts, particularly those formed by species like sargassum, offer some of the most striking examples of this temporary fertility. When storms dislodge sargassum from coastal regions, or when growth accumulates naturally in certain gyres, these mats drift far offshore. They may be small enough to cover only a few square feet, or large enough to stretch for many meters. Even a modest patch can transform the water beneath it. Young fish hide among the tangled branches. Small crabs and shrimp cling to the seaweed. Predators patrol along the edges. Birds circle overhead, searching for opportunities. For a while, the patch becomes a floating ecosystem, supporting far more life than the surrounding open water. What makes these drifting rafts so important is not just their presence, but their scarcity. In oceanic deserts, where nutrients don't concentrate easily, and where shelter is almost non-existent, any structure becomes valuable. Juvenile fish such as mahi-mahi and various species of jacks often gather beneath these seaweed mats, using them as nurseries. Even predators like tuna or sharks may linger nearby, knowing that small fish often hide in the tangled mass. The simple existence of the seaweed creates a momentary concentration of life in a place that usually disperses everything. Driftwood can have a similar effect. A single log floating in the middle of the sea may seem insignificant, but it can host entire communities. Algae may grow on it, barnacles may attach themselves to its surface, small crabs may cling to its underside, fish may shelter beneath it, even seabirds may rest on it briefly. The log, though lifeless by itself, becomes a platform for life. Its surface provides stability in an environment where almost everything is tossed about by currents. Floating carcasses, while less pleasant to think about, create some of the most dramatic temporary oases. When a whale dies and its body initially remains at the surface, it attracts predators from far distances. Sharks, large fish, and scavenging birds converge to feed. Even smaller organisms gather to take advantage of the nutrients released into the surrounding water. These events may last only hours or days, but they represent a sudden burst of energy in waters that rarely experience such abundance. Once the carcass sinks, it continues to support life in deeper regions, but its time as a floating island leaves a noticeable imprint on the surface ecosystem. Humans, often unknowingly, contribute to these temporary hotspots through debris that drifts into the open ocean. While much of this debris poses harm, some pieces inadvertently create habitat. A floating buoy or broken piece of fishing gear can accumulate algae, act as shelter for small fish, and attract predators. This is not to say such debris is beneficial, it often causes more harm than good, but it demonstrates how quickly life responds to the presence of structure. The ocean's inhabitants have evolved to take advantage of almost any opportunity, even those created accidentally. These floating islands create something like a chain of unpredictable events. A small structure attracts plankton. The plankton attract small fish. The small fish attract larger predators. The predators draw scavengers or additional visitors. Each addition brings movement, interaction, and activity to a place that, moments earlier, held only quiet drifting. Even after the structure moves on or breaks apart, the ripple of activity may influence the water for a while. Nutrients released by feeding or waste drift downward, supporting life in deeper layers. Particles shed from the floating object become part of the marine snow that feeds organisms below. Another interesting effect of these floating islands is how they alter the behaviour of passing creatures. Migratory species travelling through oceanic deserts often investigate floating structures. A sea turtle might spend hours feeding on jelly-like organisms that gather around seaweed mats. A school of fish might join the small community hiding beneath a piece of driftwood. A seabird might circle repeatedly before landing to rest. These encounters become small but meaningful breaks in the long journey across empty waters. Even though these floating oases are small in size, their impact can be disproportionate because they change the structure of the surrounding water. Currents flowing around them slow down, causing particles to settle. Zooplankton drifting near the surface may pause in the eddies created by the object's movement. A tiny accumulation of nutrients forms beneath the structure. All of these changes provide opportunities for organisms that rely on even the smallest advantage in nutrient-poor environments. Some species are so attuned to these structures that they actively seek them out. Certain fish have been observed swimming long distances to reach patches of seaweed. These behaviours reveal an awareness of the environment shaped by evolutionary experience. The open ocean does not offer reliable feeding grounds or predictable shelter, so learning to recognise and exploit even small advantages becomes crucial. The reason these floating islands seem like mirages is that they break the pattern of scarcity so suddenly. They appear without warning, they drift in and out of existence, they gather life with a speed that seems disproportionate to their size, and then, just as quickly, they vanish. A storm might break up a seaweed raft, a predator might strip a carcass of its nutrients, debris might sink or drift into new currents. When the structure disappears, the life that gathered around it disperses back into the open sea, returning to the gentle, steady rhythm of drifting. If you were to drift alongside one of these floating structures, you might think at first that you were looking at something ordinary. A tangled mass of seaweed, a discarded buoy, a log. But if you watch closely, you'd see constant activity around it. Small fish weaving in and out of the shadows, predators cruising nearby, crabs clinging to surfaces, even plankton swirling in small eddies. The entire structure becomes a living community, shaped not by permanence but by the opportunity that shelter and stability provide. The influence of these floating islands doesn't end with the organisms that gather physically around them. They also contribute to the genetic and ecological connectivity of the ocean. When larvae or small fish join these drifting habitats, they may travel far beyond their usual ranges. A young fish hiding under a piece of debris may find itself transported hundreds of miles before the object sinks. This movement disperses populations, increases genetic mixing, and spread species across vast distances. In this way, the floating islands become vehicles for ecological distribution. Another layer of importance lies in how these structures affect nutrient cycles. Even a temporary increase in feeding or waste production near a floating island can alter the chemistry of the water. Those nutrients may drift downward, providing energy to deeper organisms. They may be consumed by bacteria, which then support small predators. These small changes ripple through the ecosystem in ways that persist long after the floating island is gone. For the residents of oceanic deserts, these moments of concentrated activity can be meaningful. A jelly-like predator may feed more in a single hour near a seaweed raft than it might feed in several days drifting freely. A small fish may find protection from predators. A wandering bird may rest. These brief interactions sustain life in ways that cannot be replicated by the empty water around them. The ocean's ability to create such momentary bursts of life reminds us that even in the quietest environments, opportunity can arise unexpectedly. This pattern is not constant, it's intermittent and unpredictable, but it adds complexity to a region that otherwise seems defined by monotony. The empty waters are not as empty as they appear. They are ready to respond the moment something new drifts in. And as this journey continues, the focus shifts again from these temporary visible structures to something far smaller and more persistent. Organisms that don't rely on floating islands or brief opportunities, but quietly shape the ocean's chemistry every second, even in the most nutrient-poor waters. These tiny residents, often overlooked like plankton but different in function, act as the hidden engineers of the sea. If the drifting rafts of seaweed and fragments of debris act like brief interruptions in the emptiness of the open ocean, then the microbes living in these same waters act like something far different. They are not interruptions. They are constants. They don't appear suddenly or vanish after a short burst of activity. They are always present, always working, always shaping things in ways that most of the ocean's larger inhabitants will never notice directly. They don't gather around floating islands or wait for opportunities. Instead, they quietly transform the ocean from the inside out. Calling them small doesn't fully capture what they are. Calling them numerous doesn't either. They are the secret architects of the sea, building and maintaining systems that stretch across entire basins, even though each individual cell is so small that millions could drift through your fingers unnoticed. When you picture ocean microbes, you might imagine simple, primitive organisms that float passively in the water, contributing little beyond their own survival. But the truth is that these microscopic residents influence the chemistry, productivity, and balance of the ocean more than almost anything else living within it. They dominate the planet by sheer abundance, by efficiency, by adaptability, and by time. They were here long before larger animals emerged, and they will likely remain long after many other species have disappeared. Even in oceanic deserts, where nutrients are scarce and life seems thinly spread, microbes thrive in numbers that can only be described as staggering. To understand how they shape these vast waters, it helps to think first about how they live. Most microbes in the open ocean aren't simply drifting aimlessly. They're constantly absorbing, transforming, and recycling materials that move through the water column. Some capture light, some consume organic matter, some process chemicals that larger organisms cannot use, and some operate in ways that seem almost counterintuitive. They may be invisible to the naked eye, but collectively they act like the engine that keeps the ocean functioning. One of the most important groups of these microbial architects includes the photosynthetic bacteria that dominate much of the open ocean. Unlike larger phytoplankton, which require higher levels of nutrients, these bacteria can survive in water that offers very little. They're able to capture sunlight efficiently and use it to convert carbon dioxide into organic matter. Even though each individual cell is tiny, their global population is so immense that they contribute significantly to the planet's oxygen production and carbon balance. They perform this work quietly, drifting with the currents, dividing slowly, and persisting even when conditions seem too sparse for productivity. These microbes are specialists in making something out of almost nothing. They have evolved to use resources in ways that would not support large organisms. Some can fix nitrogen from dissolved gas, turning it into a usable form that other organisms depend on. Some can utilize trace amounts of iron or phosphorus that drift through the water in particles too small for others to absorb. Some produce pigments that allow them to harvest wavelengths of light invisible to most life. Each adaptation reflects an environment where efficiency matters more than abundance, where any unused niche becomes an opportunity, and where survival depends on the ability to process whatever the ocean provides. Because of these abilities, microbes play a major role in maintaining the ocean's nutrient cycles. Even in the emptiest waters, where nutrients are extremely limited, they work tirelessly to recycle whatever becomes available. When a larger organism releases waste, microbes break it down. When dead cells fall from the surface, microbes process them. When particles drift into deeper waters, microbes consume and transform them. This recycling is slow and constant, turning the open ocean into a giant biochemical network that supports life at every scale. You might think these processes unfold invisibly and quietly, and in many ways they do, but their effects ripple outward dramatically. For example, when microbes break down organic matter, they release nutrients that other organisms, including phytoplankton, can use. In this way, microbes help maintain a delicate balance between scarcity and productivity. Even in oceanic deserts, this recycling ensures that some nutrients remain available in small amounts, allowing life to continue. Without microbial work, the open ocean would gradually lose its ability to support even the limited productivity it has. Some microbes in these waters operate without sunlight altogether. They live deeper in the water column, relying on chemical processes that allow them to survive in environments where light cannot reach. These microbes break down organic particles that drift downward from the surface, releasing energy and nutrients that support communities in the dimmer, colder layers of the ocean. Their work forms a bridge between the surface world and the deep, even though they never travel between these realms themselves. They provide essential services simply by consuming what arrives in their environment. Other microbes specialize in transforming the chemicals that govern the ocean's acidity, oxygen levels, and nutrient availability. Some oxidize ammonia, others reduce nitrates, others break down methane, and others remove harmful compounds that could accumulate if left unchecked. These transformations allow the ocean to maintain stable conditions over long periods, supporting everything from the smallest plankton to the largest whales. Even though microbes do not move quickly or display dramatic behaviours, their chemical work creates the conditions that make life possible. The sheer abundance of microbes in these waters is another part of their story. In 1 milliliter of seawater, a volume small enough to fit in a thimble, there may be 1 million microbial cells. Multiply this across the vastness of the open ocean, and you begin to understand how their influence becomes planetary. They are not outnumbered by anything, they dominate by presence alone, and yet their individual existence is so unobtrusive that the wider ecosystem remains quiet and slow, shaped not by dramatic events but by continuous microscopic effort. Because microbes respond quickly to changes in their environment, they also reveal information about the health of the ocean. When temperatures rise, certain populations increase. When nutrients decline, others become dominant. When new substances enter the water, microbes often react first. Their sensitivity makes them indicators of patterns that larger animals might not respond to for months or years. In this sense, the microbial community acts like a feedback system, adjusting itself in ways that influence the entire marine environment. Perhaps one of the most intriguing features of microbes in oceanic deserts is their ability to adapt to patchiness. Nutrients in these waters appear unevenly. A small pulse of nitrogen or phosphorus might drift through a region, offering opportunity for only a short time. Microbes respond immediately, dividing rapidly, or altering their metabolism to take advantage of the temporary abundance. When the resource disappears again, they shift back to slower growth. This flexibility allows them to exploit conditions that larger organisms cannot respond to quickly enough. Other microbes live attached to particles that drift slowly downward. These particles, composed of dead cells, waste, and organic detritus, become tiny floating homes for microbial communities. The microbes that colonize these particles break down the material as it sinks, shaping how much organic matter reaches deeper layers. They influence the speed at which particles sink and the amount of carbon that becomes stored in the deep ocean. Their work determines how the ocean absorbs and releases carbon dioxide, linking tiny cells to global climate patterns. Some microbes form symbiotic relationships with larger organisms. For example, certain bacteria live on the surfaces of plankton or inside their cells, helping them acquire nutrients or protect themselves from harmful substances. These partnerships become essential in nutrient-poor waters, allowing organisms to survive in places that might otherwise be inhospitable. Even though the microbes receive little attention, they act as crucial companions shaping the success of their hosts. What stands out most, though, is how microbes persist even when conditions seem hostile to life. They survive at temperatures close to freezing, in waters too clear for most photosynthetic organisms to thrive, and in regions where nutrients remain scarce for years. They operate with a kind of resilience that feels almost unreal when compared to the needs of larger animals. Their survival strategies reveal how adaptable life can be when it relies on chemical flexibility rather than size or mobility. Despite being so small, they influence patterns that echo across entire ecosystems. Their steady recycling processes support the survival of zooplankton, which then support fish, which then support larger predators. A change in the microbial community can ripple upward through the food web, altering the abundance and distribution of creatures far more visible and dramatic. In this sense, microbes are neither background players nor passive participants. They are the designers of the ocean's basic functioning. If you could pause in the open ocean and examine just a small volume of water, the quiet work of these microbes would reveal itself slowly. You might see light harvesting cells absorbing sunlight, chemical processes breaking down particles, bacteria attached to tiny flakes of organic material, and countless cells dividing or drifting. The activity would seem chaotic at first, but over time you would notice patterns shaped by nutrient availability, light penetration, and chemical gradients. These patterns would mirror the structure of the ocean itself, reflecting how much of its functioning depends on consistency rather than abundance. Even though they are difficult to see, microbes help explain why the open ocean continues to function despite its low productivity. They ensure that nutrients circulate, that carbon moves through the system, that organic matter does not accumulate unchecked, and that life continues even in the quietest parts of the water column. They work without pause, without recognition, and without the dramatic movements that larger animals display, yet their influence extends farther than almost any other group of organisms. As the story of these oceanic deserts continues, the next step leads toward moments when the environment shifts briefly. These are not everyday occurrences. They are rare events, storms, mixing, unusual currents that turn stillness into activity just long enough for the emptiest waters to experience something unexpected. And these shifts reveal how the ocean responds when the calm is interrupted and life is given a temporary chance to bloom. Even in the quietest and most predictable parts of the open ocean, the environment is never entirely static. It may feel timeless when you imagine drifting through those wide blue spaces, watching the water move with steady rhythms, but the ocean is always responding to forces that build far away, unfold slowly, or appear suddenly with enough strength to reshape entire regions. Storms, shifting currents, seasonal winds, and deep water mixing events all play roles in transforming nutrient-poor waters into places where life briefly flourishes. These transformations don't happen often, and they rarely last long, but when they do occur, they reveal something important about the ocean. Even the emptiest waters are capable of sudden abundance when the right conditions come together. If you were drifting in these central regions day after day, you might begin to think that nothing ever changes. The same gentle waves roll across the surface. The same clear water stretches endlessly in every direction. The same faint particles drift downward. But beneath that appearance lies a system sensitive to forces that can build quietly, then manifest all at once. A single storm can churn the water column, stirring deeper layers upward. A shift in wind patterns can push warm surface water aside, allowing cooler, nutrient-rich water to rise. A change in surface currents can sweep nutrient pulses across hundreds of miles. These events temporarily replace scarcity with opportunity, allowing organisms to grow, feed, and reproduce with a speed that stands out against the usual slow-motion pace of the oceanic desert. Imagine a powerful storm forming far away, gathering strength as it moves across the ocean. At first, the open water responds only with slightly rougher waves, but as the storm intensifies, its winds begin to disrupt the upper layers of the sea. Waves grow taller, mixing surface water with the layers beneath. The deeper a wave reaches, the more it pulls nutrients upward from the dimmer zones where sinking particles accumulate. This upward motion breaks the usual separation between nutrient-poor surface waters and nutrient-rich depths. For a moment, sometimes hours, sometimes days, the ocean behaves differently. It becomes a stirred system rather than a layered one. For the microscopic drifters near the surface, this sudden access to deeper nutrients is transformative. Phytoplankton that have lingered in low nutrient conditions suddenly have the resources to grow more rapidly. They begin to divide, absorbing sunlight and converting the new nutrients into energy with surprising speed. The water that looked clear and empty may take on a slight green tint as these tiny organisms increase in number. They don't need long to change the character of the ecosystem. A single burst of nutrients can set off a chain reaction, creating temporary blooms that ripple outward. When phytoplankton populations rise, the organisms that feed on them respond as well. Zooplankton that drift near the surface encounter more food in a few hours than they might typically find in several days. They feed, grow, reproduce, and gather in numbers that would be impossible during normal conditions. Their own movement through the water column changes as well. Rather than relying on sparse and scattered resources, they can take advantage of the abundance while it lasts. Juvenile fish and larvae of larger species also take advantage of these brief surges, using the increased food supply to grow faster and strengthen themselves for life in a region usually defined by scarcity. Predators notice the change too. Small fish respond to the presence of zooplankton, gathering in schools that move through the water with renewed activity. Larger fish, including tuna, mahi-mahi, and various pelagic species, may shift their travel patterns to remain near areas where prey becomes more abundant. Birds circling above the ocean detect subtle shifts in water colour or movement that signal increased feeding activity below, and they descend in search of food. Even mammals like dolphins may pass through areas impacted by storm-driven productivity, feeding on fish attracted to the blooms. These bursts of life don't turn the ocean into a permanently rich environment. They simply create windows where the usual rules momentarily change. An oceanic desert blooming after a storm is like a dry landscape experiencing rain. Life responds quickly because the window is brief. Creatures that have learned to endure scarcity know how to take advantage of abundance when it appears. They feed as much as possible while resources remain accessible, storing energy or growing rapidly before the environment returns to its more familiar quiet. Not every burst of life is caused by storms. Some are driven by shifting currents, especially those that transport water from nutrient-rich areas into nutrient-poor ones. When a current carrying deep or coastal water drifts into the open ocean, it brings with it a pulse of nutrients that can support blooms of phytoplankton. These pulses may move slowly, stretching across hundreds of miles, dissipating gradually as they mix with clearer water. Organisms that drift into these zones experience a sudden improvement in feeding conditions, even if the change lasts only long enough for a brief period of growth. Sometimes, these nutrient pulses originate from far below. Deep water mixing can occur when temperatures shift or when currents destabilize layers that normally remain separate. Cold, nutrient-laden water rises toward the surface, bringing with it the ingredients needed for photosynthesis. The water may still look clear, especially compared to coastal regions, but the subtle increase in nutrients is enough to set off a temporary increase in productivity. Microbes respond first, followed by phytoplankton, then zooplankton, then everything feeding on those zooplankton. The chain reaction unfolds with remarkable consistency. Seasonal winds are another force that can cause the desert to bloom. In some parts of the ocean, winds shift direction or intensity at certain times of year, pushing surface water aside and allowing deeper water to rise. This process, known as upwelling, is most dramatic near coastlines, but weaker versions occur even in open ocean gyres. While the effect is subtle in oceanic deserts, it can still provide enough nutrients to trigger small, short-lived increases in biological activity. Even a slight rise in nutrient concentration can cause noticeable changes in the behavior of organisms. Certain weather patterns, like large-scale climate oscillations, also influence these sudden blooms. Events such as El Niño and La Niña alter wind patterns, water temperature, and nutrient distribution across wide regions of the Pacific. When nutrient-rich waters spread into typically sparse regions, blooms become possible. When nutrient-poor waters spread into productive regions, productivity can decline. These cycles demonstrate how interconnected the ocean is, how a shift in one area can influence life thousands of miles away. One of the most fascinating aspects of these sudden blooms is how quickly they fade. The same nutrients that fuel rapid growth are consumed just as rapidly. Phytoplankton multiply until the available nutrients run out. Zooplankton feed until the phytoplankton population declines. Predators feed until the prey disperses. The entire system expands and contracts in a matter of days or weeks. When the nutrients disappear, the open ocean returns to its usual state. The water clears again. The activity fades. The slow-motion rhythm returns. Microbes continue to work quietly in the background, recycling the organic matter produced during the bloom. Some of that matter sinks, becoming marine snow that supports deeper ecosystems. Some is consumed near the surface. Some becomes part of the bodies of animals that soon drift back into lower nutrient conditions, carrying the benefits of the bloom with them. In this way, even short-lived pulses contribute to the long-term functioning of the ocean. If you were drifting through these waters during a bloom, you might not notice anything dramatic at first. The water might take on a slightly different hue. You might see more tiny particles drifting near the surface. The behavior of small fish might shift, becoming more energetic. Birds might circle more frequently overhead, but the bloom would still seem understated compared to the dramatic scenes found in more productive regions. The open ocean never bursts into chaos, even when conditions temporarily improve. Its reactions remain measured, shaped by the fact that most organisms here are adapted to scarcity, not abundance. Still, the blooms matter. They offer brief opportunities for growth, reproduction, and feeding. They allow organisms to store energy that helps them survive the long periods between nutrient pulses. They create moments when life becomes more visible, more active, more interconnected. And they remind us that even the emptiest waters depend on forces that operate far beyond their boundaries. Storms forming hundreds of miles away, wind patterns shifting across hemispheres, currents tracing ancient paths. These events also show how sensitive the ocean is to environmental change. A slight shift in water temperature or wind direction can alter productivity across thousands of miles. A storm that stirs the surface for a few hours can support life for weeks. A current that carries nutrients into an empty region can reshape feeding patterns. These processes illustrate the ocean's dynamic nature, even in places that seem still. As the story continues, these blooms lead us to a deeper understanding of how humans influence the oceanic deserts. If natural forces can transform scarcity into abundance, human activity can do the same. but often in ways that disrupt rather than support the delicate balance. And this influence becomes clearer as we explore how our presence, even far from land, shifts the rhythm of the quietest waters on Earth. When you imagine the Central Ocean, far from any coastline or visible human presence, it's tempting to think of it as a place beyond our reach, a place too remote, too empty, too self-contained to be shaped by human activity in any meaningful way. After all, these waters hold no cities, no boats most of the time, no structures anchored to the seafloor, and no signs of development. They stretch across thousands of miles where wind and current seem like the only forces that matter. But as quiet as these regions are, and as slow-moving as their life tends to be, the human shadow still reaches them. It doesn't arrive in the obvious ways you might see near coasts. No dredging, no harbours, no fishing fleets clustered in narrow channels. Instead, it spreads through diffuse, persistent threads, chemical traces, drifting waste, noise carried farther than expected, and changes in temperature that unfold across decades. Even in the emptiest waters on Earth, the presence of people is woven into the background. One of the most noticeable ways humans influence these waters is through the debris that travels farther than anyone intended. A single piece of plastic dropped on a beach may drift for years before settling into the open ocean. Fishing gear lost during storms can wander across entire basins. Small fragments of packaging, ropes, nets, and containers join the circulation patterns of global currents. These objects don't move with purpose, but they persist in the same way natural floating islands do. The difference is that they don't break down easily and often remain long after any organism that depended on them has moved on. For the creatures living in these waters, these drifting objects create opportunities and hazards at the same time. Small fish or juvenile organisms may gather beneath a floating piece of debris, using it as shelter the way they would use seaweed. But unlike natural rafts, human-made objects don't always behave predictably. They may entangle animals, restrict movement, or introduce sharp edges into places where delicate tissues dominate. And because the debris can last for years, it can carry species far beyond their normal ranges, introducing them to environments they are not adapted to and shifting ecological balances in subtle ways. Even smaller fragments, microplastics, have become part of the marine environment. These particles are easy to overlook, even when present in large numbers. But microbes grow on them, zooplankton ingest them, and small fish consume them. In the open ocean, where food is scarce, anything resembling a particle of organic matter may be eaten, even if it offers no nutritional value. Over time, these artificial fragments circulate through food webs that were never meant to include them. They become part of the drifting world, influencing organisms that cannot distinguish between what sustains them and what merely occupies space. But physical debris is only one thread of the human shadow. Chemical traces travel even farther. Industrial activities release substances that eventually enter rivers, then coastlines, then open water. Some chemicals break down quickly, but others persist for decades, circulating through the deepest gyres and drifting across multiple basins. In regions where nutrients are scarce, even tiny amounts of unfamiliar chemicals can have outsized effects. Microbes may respond to them by shifting their metabolic processes, plankton may grow differently, and predators may accumulate them slowly over time. These changes are often invisible, but they alter the baseline conditions of the open ocean in ways that didn't exist before human influence. Climate change adds another layer of complexity. The emptiest waters may seem too remote to feel the effects of rising temperatures, but they respond all the same. A slight warming of surface waters alters density, which affects how layers mix. When water layers mix less easily, nutrients struggle to rise from the depths, making already sparse conditions even more challenging. The organisms that depend on rare nutrient pulses may find those pulses occurring less frequently or with less intensity. Phytoplankton grow more slowly. Zooplankton populations shift in composition, Predators move toward other regions in search of more consistent feeding grounds. In some areas, warming causes waters to expand and strengthen the circular currents that define ocean gyres. These strengthened gyres trap more debris and alter distribution patterns of plankton. What was once a gentle drift becomes more isolated, making certain regions feel even more barren. The organisms living in these gyres must adapt to changes that unfold slowly but steadily, adjusting their pace of life to new norms shaped not by natural forces, but by distant human activity. Fishing pressure also influences these waters, even when fishing vessels rarely enter the Central Ocean. Many species that migrate through oceanic deserts, tuna, sharks, billfish, are targeted heavily in more productive areas. Their populations decline far from the places we imagine them travelling through. When fewer individuals undertake long migrations, their presence in oceanic deserts becomes even more fleeting. A predator that once passed through regularly may now appear only occasionally. This changes interaction patterns with resident species, shifts feeding dynamics, and alters how energy flows through these already sparse ecosystems. By reducing the abundance of certain migratory species, humans indirectly influence the experience of life in the open ocean. A school of tuna no longer passes through as often. A single shark's patrol route becomes longer and more sporadic. Predators that once helped regulate certain populations may no longer be present frequently enough to maintain the same dynamics. Even though these shifts may seem small, they accumulate over time, changing the rhythm of the region. Noise pollution also plays a role, though it might be surprising to think of noise in a place so remote. Ships crossing international waters, cargo vessels transporting goods, tankers, research boats, and fishing fleets all generate constant low-frequency sound that travels immense distances through the water. Unlike noise in air, which dissipates quickly, sound in water can travel hundreds of miles. Even a distant ship can create a steady hum that becomes part of the acoustic environment. For creatures that rely on sound to navigate or locate prey, this added noise complicates their world. They must sift through background vibrations to interpret the signals that matter. In an environment defined by quiet, the intrusion of persistent sound becomes another reminder that no part of the ocean is entirely untouched. There is also the matter of nutrient pollution. It might seem counterintuitive that nutrient-poor waters could receive excess nutrients, but currents eventually distribute everything. Runoff from agriculture, wastewater, and industrial processes can enter major currents that carry these materials across large distances. When even small amounts of extra nutrients reach the open ocean, they can produce temporary blooms in places where natural blooms are rare. At first, this may seem beneficial, offering extra resources to organisms that depend on them, but human-derived nutrients don't spread evenly, and they may favour certain microbes or algae over others, shifting long-standing balances. The organisms that thrive under these conditions might not support the same food webs, creating subtle mismatches between species that evolved together for thousands of years. Temperature changes also influence the movement of entire water masses. When polar waters warm, currents can weaken or shift. When surface layers warm, they expand. These shifts alter the pathways that migratory species rely on, sometimes forcing them into less favourable regions. A predator that once followed a predictable path may find itself navigating water that no longer provides enough food. A species that depended on a specific temperature range may now extend its journey farther north or south. These adjustments ripple across the food web, influencing interactions between species that might meet less often or in different contexts. Another part of the human shadow lies in the simple fact that the open ocean is increasingly monitored. While research itself is not harmful, the presence of scientific equipment, sensors, drifting buoys, or automated floats adds new forms of structure to the water column. Some of these devices become temporary homes for microbes or small organisms, similar to natural floating debris. They create microhabitats that wouldn't otherwise exist. Though the impacts are usually small, they remind us that even well-intentioned activities leave traces in the quietest places. There are also human-driven shifts in atmospheric circulation that influence rainfall, wind patterns, and ocean mixing. These changes may strengthen or weaken the forces that create nutrient pulses. They may alter the timing of seasonal winds. They may increase or decrease the frequency of storms that stir the water. Each shift affects how often the desert blooms, how long the blooms last, and how life responds to them. Even subtle alterations in evaporation and precipitation can influence salinity levels, which in turn influence density gradients between water layers. These gradients determine how easily nutrients move upward. If salinity shifts slightly, the layering of the ocean changes, affecting everything from microbial growth to the movement of fish. Though these changes unfold slowly, they are cumulative, shaping the environment in ways that will persist for generations. The human shadow becomes most visible not in any single event, but in the slow accumulation of many influences. A degree of warming here, a shift in current strength there, a rise in microplastic concentration, a reduction in migratory predators, a slight increase in nutrient pulses from runoff, a constant hum of noise. Each change by itself may seem small. Together they form a quiet, persistent pressure that shapes even the emptiest waters. If you imagine drifting with the resident creatures of the oceanic desert, watching the slow pace of their lives, you might not notice these influences as they unfold. You might see a piece of debris, drifting just like natural rafts. You might feel a slight temperature difference from one day to the next. You might detect a hum travelling through the water. But the full pattern becomes visible only when you step back and consider how life in these regions today differs from life centuries ago. The ocean still functions, still supports its slow, sparse patterns, but those patterns have been nudged into new trajectories. Yet, despite the reach of the human shadow, the emptiest waters are still resilient. The microbes continue their steady work. The drifters still move with the currents. The predators still patrol with patience. The visitors from fuller seas still pass through on their migrations. The rare blooms still happen when storms and mixing events align. Life persists, adjusts and adapts. These waters hold a kind of endurance that comes from existing in scarcity for millions of years. As the journey continues, the final step turns toward the long view, toward how these vast, quiet waters endure through change, and what it means to recognize their resilience in a world where everything, even the deepest calm, continues to evolve. If you followed this slow drift across the emptiest waters on Earth, you may have noticed that something changes in the way you imagine the world out here. What began as a picture of stillness, scarcity, and distance gradually becomes something richer and more layered. The oceanic deserts are not empty after all. They are quiet, yes. They are sparse, yes. But they hold rhythms that continue whether we witness them or not, shaped by creatures that drift without complaint, predators that move with a restrained purpose, microbes that work tirelessly in the background, and travellers that pass through without leaving a trail. As remote as these regions are, they create a kind of calm that is deeper than silence. A calm that emerges not from the absence of life, but from the way life here has adapted to pace itself. Staying with this world long enough makes it easier to see why the stillness of the open ocean feels so different from stillness on land. Out here, stillness isn't an interruption or a pause. It's the default state. It's woven into every movement and every moment. The water rarely rushes. The animals rarely hurry. The changes happen gradually, unfolding across hours, days, or seasons. Even storms, when they arrive, offer disruptions that fade just as steadily as they appear. The oceanic deserts don't resist stillness. They accept it as part of their structure, shaping every creature that lives within them. And if you reflect on that for a moment, it becomes clear that this slow, spacious environment has something to offer us too. Not as a metaphor we're meant to force into our lives, but as a contrast that highlights how differently time and movement unfold depending on the environment. Most of us live in places where noise and activity seem constant, where demands pull our attention in multiple directions, where rest feels like the exception rather than the rule. But the open ocean reminds us that an entire world exists where slow pacing is not only normal, but necessary. Spend long enough imagining the creatures of the oceanic desert, the plankton drifting with the currents, the predators conserving their energy, the microbes working quietly every second, and you start to recognize patterns that echo how we experience our own quiet moments. When the world around us becomes hectic, stillness can feel uncomfortable or unfamiliar. But when we choose to slow down, even briefly, our thoughts often rearrange themselves into something clearer. We begin noticing the spaces between things rather than only the things themselves. In a way, the oceanic deserts demonstrate how much can happen when very little appears to be happening. The microbes continue transforming chemicals. The zooplankton rise and fall with the light. The drifters feed in tiny increments. The predators wait patiently for the right moment. Everything moves, just not quickly. Everything changes, just not dramatically. And perhaps that's one of the reasons these waters feel so calming to imagine. They show that progress doesn't always require urgency, that life can thrive in its own quiet way, even when resources are thin and movement is slow. If you picture yourself floating in these wide blue spaces, far from shore, noticing nothing but the horizon and the movement of the water beneath you, the experience may feel like a kind of reset. There's no constant stimulation, no immediate demand, no rushing. There is only gentle motion and the knowledge that beneath the surface, life continues steadily without the need for intensity. The creatures here have learned to stretch their energy, to make the most of whatever drifts their way, to endure long periods without reward, and then seize opportunities when they arise. That endurance reflects something deeply practical rather than philosophical, living efficiently in a world defined by scarcity. Thinking about these waters in that way can shift the way we think about our own lives. Many of us spend our days in environments filled with choices, alerts, schedules, noise, and momentum that pushes us forward, whether we're ready or not. But the oceanic desert suggests that meaning doesn't always come from abundance. Sometimes it comes from pacing ourselves, from knowing when to move and when to rest, from understanding that not every moment needs to be filled in order to be valuable. These empty waters also reveal the quiet importance of consistency. The microbes that shape the ocean do not work in bursts. They work continuously. Their influence accumulates slowly, creating stability that supports everything above them. In our own lives, the small, consistent efforts, resting well, being kind, showing patience, tending to responsibilities without rushing, often shape outcomes more reliably than dramatic, short-lived bursts of activity. The ocean doesn't hurry, and yet it accomplishes everything it needs to. Microbes also remind us that the smallest actions can have wide-reaching effects. In the open ocean, a single bacterial cell may alter the chemical balance around it, influencing the growth of other organisms in ways that ripple outward. On a completely different scale, our small behaviours can influence how our days feel, how others respond to us, and how we shape our environments. The impact doesn't need to be visible to be meaningful. It just needs to be steady enough to matter over time. Then there's the way these waters respond to rare pulses of abundance. When storms stir the nutrients, or currents bring unexpected richness, life reacts quickly but wisely. Organisms feed, grow, and store energy, but they don't shift their entire lifestyle based on a temporary change. They know the abundance won't last. They appreciate it without relying on it. For us, those moments of excitement or opportunity can resemble those oceanic blooms. They are worth celebrating, worth using, worth enjoying. But they do not replace the slower rhythm of daily life. They fit into it. Even the migrating creatures that pass through these waters teach us something about movement and purpose. They travel long distances not because they want to avoid quiet, but because their lives depend on pacing across wide spaces. They move steadily, cover great distances using efficient measured strokes, and rest in the calm when needed. They do not resist the emptiness of the ocean, they incorporate it into their journeys. The quiet becomes part of the path rather than a barrier. The floating islands, the brief oases created by seaweed or driftwood, offer their own gentle insight. Life gathers around opportunities, even small ones, and disperses again when they fade. In our own lives, temporary points of connection, support, or inspiration appear and vanish too. We gather around them while they last, then continue onward, carrying the influence with us. Nothing remains static, yet the movement remains steady. Perhaps the most powerful lesson these waters offer is that stillness doesn't have to mean emptiness. It can mean spaciousness. It can mean openness to small details. It can mean noticing patterns that constant motion obscures. The oceanic deserts show us that stillness is not a void. It is a context, a quiet canvas where subtle forms of life can reveal themselves. When you imagine the pale blue clarity of these waters, stretching with no visible boundaries, you might feel a sense of scale that's difficult to encounter anywhere else. These vast spaces exist without needing to prove anything. They hold depth and structure even when they appear barren. They support life that persists in quiet ways. They remind us that calm environments aren't lesser, they're simply different. And within this calm, connection becomes easier to see. Every drifting particle, every migrating traveller, every microbial transformation, every rare pulse of nutrients ultimately ties back into a larger network that spans the entire planet. The quietest waters are not isolated. They are connected by currents, winds, cycles and migrations to every coastline, every reef, every polar sea. Even though they feel remote, they influence everything else. Their stillness becomes part of a global rhythm. In a similar way, the calm moments in our own lives connect us to everything else we do. They let us regain energy, reflect, observe, and prepare for the next movement. They support the busier moments the same way the ocean's slow pace supports the occasional bloom of life. Stillness is not separate from action. It is what makes action sustainable. If you imagine yourself settling into a quiet moment, listening to soft sounds, breathing at a comfortable pace, it isn't so different from imagining the oceanic desert drifting beneath a wide sky. There is enough space for thoughts to move without urgency, enough quiet for subtle details to come into focus, enough depth for things to develop gradually. Stillness doesn't need to be dramatic, it just needs to be allowed. The quietest waters on Earth endure not because they resist change, but because they absorb it slowly, integrate it, and continue forward. They persist through storms, warming, drifting debris, and shifting migrations. They adapt not with panic, but with patience. That resilience offers a kind of reassurance that life, even in its calmest forms, can withstand far more than it appears. And as this slow exploration nears its resting point, the open ocean remains there in your imagination, blue, wide, steady and unhurried. Not concluded, not wrapped up, just continuing the same way it always has. A gentle reminder that stillness can be a strength, that quiet can hold meaning, and that even the emptiest places contain life moving at a pace that keeps everything connected.